Yeah, hi, good evening, everyone. So, welcome to week 3 open session. First, I hope you have watched the videos of the week 3. So, today we will discuss the content of week 3. Before starting, if anyone have any specific doubt in week 3 or any query or any specific topic which you want to uh, learn, discuss in today's session. Yeah, am I audible? Okay,
Yes, sir, you are audible, sir.
okay, okay, thanks.
No one is acknowledging.
Yeah, no problem. Okay. So no query from your side. Any specific topic, any specific doubt? If you have, please ask. Uh,
So I,
Otherwise, then
I could not finish the week 3. I was still going through the week 2, but I plan to finish before this coming Saturday, Sunday.
okay, okay, fine. So no problem, and then we will discuss the all topics of the week 3. So meanwhile, if you have any doubt, any in any topic, so you can ask. Okay. So I'll summarize all the topics of week 3. Let's share my screen.
Sir,
Yeah, Prince.
yeah, sir, the week two PPA 6, right? PPA question number 6. I mean, just to understand how to
Mhm.
approach it.
Okay, okay.
I mean, at the end of the session or whenever.
Yeah, no problems. We can discuss initial of no worries.
So
Week
this,
two practice assignment
sir,
6.
one doubt. This live coding problem we were discussing. It is only
Hmm.
released for week 1 and 2. Week 3 is yet to come, right?
Yeah, Friday. This Friday it will release.
Okay, okay.
So every Friday actually we are releasing these problems during the live session on the Replit first, then on the portal. Okay, so this Friday actually week 3 live coding session will be there, and at that time week 3 problem will be released. Okay, so problem number 6, you are saying this one, correct?
Yes, sir.
Hmm. Okay. Okay. So this type of problem, so here some omega is also given. Do you know omega meaning? This omega big O, what is the meaning of this, and what is the rule for complexity?
Yes, sir. I mean, omega is the lower bound.
Yeah, lower bound. Okay.
Theta
So
is the tight bound middle value.
yes, yes. So I'm just creating one graph for to explain this. So we have this function for any algorithm. So fn is given something, and we want to calculate the complexity for given function fn. So for big O notation, omega notation, and theta notation, what is this? And when we use these notations, so what happen actually? Suppose if our fn function is like this, okay, so this is fn, okay, and if we can figure out upper bound for this, okay, so so this is input line, so this is input line, and we are passing some input. This is from 0 to, we are increasing this side, and this is the time, okay. And so this fn function, if suppose if we figure out any function like gn, and this is one constant, so any upper bound, if fn is given, for this fn we figure out any cgn, another function gn, where the c is constant, which will always be greater than this fn after some point, input point like this. So this is the point here, we can see that this is n0 point. After some input value, this cgn will always be lie above or equal to this fn, but it will not come below this fn. So if we can prove this, so that means we can write the complexity for our function like this fn equal to big O gn. Okay, so if we can prove this, if we can figure out any cgn function which is always greater than after this n0 input compared to this fn, so we can write the complexity with big O gn. So that means this is the upper bound. This gn function is with some constant c. It will always be greater than to this fn function, greater than or equal to. So condition to write the complexity in this with the big O notations, this condition should be satisfied. So this fn should always be less than equal to this cgn. Okay, so if this condition is true, you can write the complexity with big O notation. Okay, similarly, yeah, okay. So for omega notation, so suppose in the similar things, suppose this is fn function and cgn. Okay, so same thing, c here, c is a constant. And suppose if we can figure out any gn function for given fn function which is always lower and equal to this fn function after some input n naught. Okay, so this cgn will never be move greater than this fn, okay, above side. So if we can prove this, so we know that this is a lower bound. Okay, lower bound. So our fn can go till this point or it can go up. So but we don't know what is the upper side, but we have figured out this lower things. So we can represent the complexity here. We can write this condition like this. So fn is always greater than equal to cgn. Okay, if this condition is true, then we can write the complexity fn equal to omega and this gn like this. Okay, and third condition is if we can figure out both bound fn, if we can figure out c1gn and if we can figure out c2gn. Okay, so here this fn will always be lies in between the c1gn or c2gn. So this is the upper bound and this is the lower bound. If we can figure out both upper bound and lower bound for any function, then we can write the complexity with theta notation. So the formula for this is fn is always greater than to c2gn and less than equal to c1gn. Okay, if this condition is true, then we can write the complexity fn equal to theta gn. Okay, so these are three conditions. We know that. So here this gn, this may be always greater than to fn or equal to this fn. So this, then we can use this big O notation. With the omega notation, that means this should be smaller than this fn or equal to this fn. So then we can use this omega notation. Okay, and here theta we are using, that means this this gn should be lies between, so this gn will be equal to this actually fn, because here we are using both bound. So this gn or fn should be same, or we can say that this is lies between cgn, c1gn or c2gn. Okay, so most of the time with the theta notation, this is actually same, because we cannot write bigger value here. Okay, because that will violate the condition then. So here in this problem, you know that big O is given and omega is given someplace. Okay, so we should know. So in the case of big O notation, so that means this should be greater than to fn or equal to fn. Okay, and here if it is given with omega notation, so this gn should be less than to fn or equal to fn. Now this is the required things to check. Now if three functions are given here, okay, so fn, gn and hn. Now just figure out that which value is what is the order of the value which is given here, or what is the order of complexity? Which one is greater, which one is smaller? So can you figure out this? So here do not apply any smaller value of n. Okay, so just think about the large input,
The
largest
largest
input.
is based on h of n.
Sorry?
Largest would be h of n. Largest would be h of n.
H of n. You are saying this is the largest.
Yes, sir.
Why not this 2 to the power log n?
It would come to n log n, right?
Sir, it will grow very slow.
No, but if this log n value is actually very big, suppose if this n is too much big and we calculate the log n for this, then it will become also big value. Okay. So in the complexity, you have already seen that what is the order of complexity like? Is smallest is log n, then next bigger is like n. Okay, or first is constant log n, then n log n, and then n square, then n q, like this. And if this 2 to the power comes in the last to the power n. Okay, so this is the highest complexity, biggest complexity. If this log n is actually very big value, then in that case, just figure out that which one is the biggest value here. Okay, so here do not put any small value for n, because just consider that this log n is the largest, biggest value, and n will be that 2 to the power these things. Okay, so how you are getting this log n value for any thing? You are getting like this 2 to the power log base 2. What is the formula to calculate? Okay, so suppose if you are 1024, you are writing this 10 to the power 10, sorry, to the power 10. Okay, and we have this log n. If we are taking this log here, so this base and this is base, this 10 is coming here, and we are getting this log n value. Okay, so here if for 1024 we are getting this log n value 10. Okay, similarly if this value is very big, okay, and so this will also be big. Okay, log n value will also be big. So in that case, just consider that this log n is the largest value. So in that case, which one will be the biggest value here? So this 2 to the power actually log n, this is 2 to the power log n. So this is actually increase very fast. If you are increasing the value of this, so suppose what is the 2 to the power 10, then if you increase this 2 to the power 11, it will increase very fast. Okay, 10 to the power 12. So this value is increased very fast corresponding to the input. So this is considered as a greatest value, 2 to the power 6.
Won't that be equal to n? Like, say, if you're taking n equal to 1024, log of 1024 will be 10, right? So the whole value will be 2 raised to 10. So we are getting 1024 back. It will be like n, right? N, like.
It is n log n only, sir. I tried with the graph also. So f of n is.
No, what value you took for the graph? What is the maximum value you took?
No, sir. Like
Just the graph.
that. If you are like, if we e raised to log e raised to something, that will become like just that value, right? It's same way 2 raised to log 2 base. The base is 2 there, right? The whole value will be n, right? So it will be n log n.
No, suppose if you are getting log n value equal to 1024, okay, for some value. So what will be the value for that 2 to the power 1024, correct?
No.
For this value, you will get this log n.
Sir, take n as 1024.
Hmm?
Take
What?
n as 1024. We can start from n equal to 1024.
No, this is a very small value actually.
No, I'm just saying if it's
So-
1024, then log n we will get as 10, right?
So log n will be 10, correct.
So 2 raised to 10, we will get the value back as 2 raised to, the whole value will be 2 raised to 10 till 1024. So we are getting back that n value.
Okay, so you are getting 2 to the power 10 and then log n. So log n, that means 1024 into 10. You are getting this value for fn.
Yeah,
And
so
what you are getting for the next? Okay, so this gn, what you are getting gn, then 1024 and log n. So that means what is the log n? This log n, that means this is 10. Okay, and what is the log value for 10? So this is near to 3.
Yeah.
This is near to 3. Okay,
Yeah.
so that means 1003, like this. Okay, and what about this hn? So this is n equal to 1024 and log n will be 10 into 10. Okay, so now you are feeling that this is the bigger value, correct?
Yeah.
But this is not true always, because so you are actually thinking for the small value, but if you will increase the value of this log n value, so let me just check for like this. Suppose we have a n value, this 2 to the power 1024, and we are getting log n value 1024. Okay, so in that case you will get 2 to the power 1024. Okay, here we are considering log n equal to 1024 and n equal to 2 to the power 1024. Okay, we are considering this. So 2 log n, this is the value, into, and next is log n. So log n, we have this 1024. So this we are getting for first function. Second function, n log n. So n, we have this 2 to the power 1024 into, so that log n. So this is 1024 log and log n. This is 1024. So this will come 10. Okay, and next is this n into log n square. So n here 2 to the power 1024 and into uh, log n square. So log n is 1024 into 1024. So here we are getting this value. Okay. So check. So n and log n square. And n is here. N is here and log n.
We can write the first one as n into log n, and here we are doing n into log n into log n. So hn will be higher than the fn, right?
Okay. So n, okay, log n, we're taking n log n square. So n will be this log n, and this is log n. Log n square is log n is 1024 and 1024. Yeah, so then this is okay. So you are looking like h is greater than. Okay, so are you getting incorrect answer for if you're considering this hn is the greatest value? Because if hn is greatest, then answer should be so this hn is the greatest, then fn, and then gn. Okay, if we consider this, so which function is correct? So fn equal to big O gn, fn equal to big O gn. So gn should be greater, but this is not true. Okay, fn equal to omega gn. So fn equal to omega gn. Yeah, this is lower, so we can write this. And gn equal to big O hn. So gn equal to big O hn. Yeah, this is okay. So gn equal to big O fn, and gn equal to big O fn. So gn equal to big O fn. Yeah, this is greater. Correct. hn equal to big O fn. No, this is not correct. This is less. So this is not correct. Gn equal to big O fn. So gn equal to big O fn. Yeah, this is greater. So this is okay. But hn equal to big O fn. hn equal to big O fn. So this is smaller fn. So this cannot become. So answer is B. So is it B answer is correct or?
Yes, sir.
Fn equal to okay, so B answer is correct. Yeah, so this Hn is we are getting higher. Correct. So after calculating, yeah, we are getting this way. So if any value, if we take in for log n, so definitely this 2 times multiplication will be there, and at the above only 1 time multiplication is there. So we will get this one is the highest. And after that, you got how I am calculating that answer is correct or not? I'm just checking the condition in the each option fn equal to big O gn. So that means if you are using big O signs, so that means this gn should be greater or equal to this fn. Okay, so in order I'm checking this. So gn is coming here, lowest one. Okay, so fn is the bigger one. This okay, so we cannot take smaller value inside the with the big O compared to the fn. So because of that, this is wrong. Okay, then this is wrong, so complete option we can ignore. So fn equal to omega gn, so that means this should be less than to fn. So here gn is the less than to fn, so this is true. And this gn equal to big O hn, so hn is should be greater than this gn, so hn is greater than to gn. So yeah, both are true in this statement. Okay, so after getting the order, just check this relation, the complexity.
Got it. Thank you.
Okay. Yeah. Okay. So any other query in this week 2? Any other question? Or
Sir, this problem which you solved now and explained, what we understand from this, like in the real time, some piece of code, how we can take this to real time coding? I mean, how we have to understand that?
no, this actually this type of complexity maybe you got for some very complex algorithms. Okay, so not general algorithms which we are learning in the course. Okay, what we are learning in the course that are actually polynomial algorithm. Most of the algorithms are polynomial, so you will see the complexity which are actually like n to the power, or this n log n square, or this log n. This type of complexity you will get for the normal algorithms, normal code. But some possibility is there if for any complex algorithm which is designed for some any specific purpose. So maybe this type of complexity you will get. This is exponential. This 2 to the power log n is actually exponential complexity. So this really actually we got very generally we got this type of complexity for hard problems. So that this types of problems will be defined in the week 11. So there are some problems so where actually we have no polynomial solution. So that problems considered inside the hard problem. So on for that problems actually we get the complexity in this exponential time.
Okay, so sir, is it like if some coding, if some function is the fn, and it can be interpreted as c into g of x,
Mhm.
should we understand this way that the time complexity of that will be big O of g of n?
So actually, generally we use the big O notation because we only interested in the worst case things. But how we calculate the complexity with notation? So like suppose if any function is given fn equal to 2n square plus 3. Okay, this function is given. So how we can write the complexity? Which notation we can use with for this function? Okay, so what we will do? We will just try to prove the condition. Okay, and we will figure out that for any n input, uh, if we can figure out, if we can calculate the upper bound for this function. So how we can do this? So we are just proving that can we write this fn equal to big O, this what is the highest magnitude of n is n square. Okay, so we takes this as a complexity. So fn equal to big O n square, can we prove this? So for proving this, we will figure out, we will calculate the cgn above that upper bound. Okay, so how we can calculate? So fn equal to 2n square plus 3. Okay, so now can we figure out any greater than value, and we can replace this 3 by n. Okay, if I replace this 3 by n, so I can write like this, so 2n square plus n. Okay, and I am taking the value n is greater than equal to 3. So this is n is equal to n is representing here input. Okay, so can we write this equation? So for n is greater than equal to 3, this side will always be greater than or equal to this side. Correct? If I am taking n equal to 3 here, so this will replace by 3, so both will be equal. But if I am taking n equal to 4, then this will become 2n square plus 4. Okay, but this will remain 2n square plus 3. So that means this side now it is greater. So what we are trying to do, actually, we are just reducing this complete expression in the terms of the highest order of n. Okay, now I can write this as a equal to 3n square. Okay, 3n square. So I have just written this as a 3n square. Now this is reduced in one term. Okay, 3n square. So here, what is this 3? We can use as c, constant, and this n square is a gn. Okay, now
But
we can say that,
sir, how we are writing, because it is 2n square plus n, that cannot be written as 3n square, right? I mean,
no, this is okay. Okay, I have written n. Sorry. I think I should written this n square. Okay, n square. Okay. Actually, I wanted to convert this term in. I want to reduce this term into the highest order of n. Okay, this one. So I can write like this. So n square value should be greater than equal to 3. Okay. So if I'm taking n square, if I replace this n square equal to 3, then this value will always be equal to. Okay. If I'm taking this n square value equal to 2, n square value equal to 2, that means 4. So that means n should be 2. Okay. So for this case, this will be greater than. So we can prove in this way. So, okay, so for every value of which is greater than this, n square equal to 3, if I am taking any greater than this value, this part will always be greater than to this part. Okay, now we can write this as a 3n square. So 3n square, now we can compare this like as a cgn. So here this 3n square is actually a upper bound, and we are just writing is a c in the form of gn. And then we can write this condition. So the cgn, actually cgn is greater than equal to fn. For which value? N naught, here we will consider as a this 2 we can take. Okay, so n naught, here n square we have calculated 3, and n square is greater than equal to 4, so we can consider as a n0 equal to 2. So what is the square root value for this? So if we take n naught equal to 2 or greater than this, okay, so this is now point which I have created in this graph. So this point, okay, so if this n naught equal to 2, now the cgn is always greater than to this fn. So now this we have proved. So we can write the complexity for this function is fn equal to big O gn. So what is the value of gn? N square. Okay, so this n square. So this will be the complexity for this function. So with big O notation.
So are we saying by raw calculation we get that fn is equal to 2n square plus 3? Then we should interpret that as that big O is n square. Correct? The highest.
No, we have to prove this. We cannot write directly anything. Okay, if you know the proof for this, if you can prove this, if you figure out the upper bound for this for the function, then you can write. You should have proof for this. Okay. Similarly, you can also write the same complexity with omega notation. So same function like fn equal to the 2n square plus 3. And can you calculate the lower bound for this function? Okay, so we can write like this. So this function should always be greater than equal to, if I take this only this part, okay, 2n square, so 2n square, and I ignore this. Okay, so this is the function I have just calculated in the highest order of the term of n square. And now you can see for any value of n, So we can take n is greater than equal to 0. Okay. Now this will always be greater than equal to this 2n square. Correct? If you are taking
right.
Or if for any input we generally not take like this 0, so we can write like this 1. So if you are putting 1, so this is greater, 2, this is greater. Okay, because here 3 is the additional things, so this will always be greater. So now we can compare this part as a CGN. So C is a constant, so this part is a constant, and this part will be a GN. Now this will consider as a lower bound. Okay, and we have proved this.
Sir?
Yes.
Sorry to interrupt, but I have a small question here. Sir, why can't we write this as sigma of n only? Like 2n square plus 3 is greater than equal to n, which is true for all values of n.
No, that is okay. That is also correct. Okay. So for lower bound, so for any complexity, suppose if fn is given like 2n square plus 3, so you can also say that this is n, this is greater than n, correct?
Yes.
So
Sir.
yeah, you can also write the complexity for this function with omega n. Lower bound is so if you're getting, generally we calculate the closest lower bound.
Okay, sir.
Okay, so there is no upper limit. If you are calculating the complexity like here, so this is n square and function is like n square, and you are getting cn square something. So this nq is also a upper bound for this function. Okay, nq is also a upper bound. According to the rule, this fn should be less than equal to your upper bound. So in this case, this is correct. You can also take n to the power 4. So that is also correct. You can also write the complexity with big O n4. But this is a upper bound things. Your fn will never be reach this n to the power 4. So according to the property, this is correct. But generally for the complexity, we figure out the closest upper bound.
Got it, sir.
Okay, which one is the closest? If we are taking n square, so we will figure out the closest complexity n square, or
Okay,
n to n log n like this. Okay, but according to the property, all are correct. Okay, if any value which is greater than this, that is actually a upper bound, and we can use the complexity. But for complexity for any algorithm, just check the closest upper bound. Okay, so here in this second problem, we have figured out the lower bound. Then we can write the complexity with omega gn. And for the last thing, theta, if you can prove both upper bound and lower bound for any function. So like this problem 2n square things, we have proved both condition. Okay, upper bound we have proved in the previous, and lower bound we have proved. Now if both we have proved, then we can also write the complexity fn equal to theta gn. So gn is equal to n square here. Okay, like this. So all are true. Okay, all are okay according to the theoretical rule. So, but generally for the course, we are using this big O notation. So big O is generally represent. Actually, we are just trying to reduce the worst case time. So we want to reduce our upper bound for any algorithm. So we will just consider the complexity in upper bound case. Okay, so we will use this. We will always write the complexity with big O notation. Not all, but you should know what the meaning of each notation omega theta like this. Okay. Is it fine?
Yes.
Okay. So shall I move to week 3? Because week 3 is some topics someone is posted also in the discourse. Okay. So week 3 basically we have some topics. So we have first is the sorting algorithm. So one remaining sorting algorithm we have quick sort. So any query in this quick sort, because we know that the purpose of quick sort is sorting. Okay, you have already learned this 3 sort: selection sort, insertion sort, and merge sort. And this is the remaining one more sort, quick sort. So this is the one topic which is from previous week, but that due to duration of the lectures, it is shifted to the week 3. And another topic is linked list, stack, queue, and hashing. These are the main topic of the week 3. Okay, which are new. So any query in the quick sort? Anyone?
Sir, I didn't quite understand the code implementation of sort.
Okay, so have you understand the concept?
Yes, sir. The theory part was I understood it, but I couldn't
So
map it to the coding.
why you are looking the code? If concept is clear, just try to write your own code.
Okay.
Okay, we always suggested that if the concept is clear of the algorithms, just try to write your code, because this is just a code which is written by someone else. Okay, so maybe the writing style may be difficult, or some function someone is using which you are not able to understand. But if you can try by your own in your own style, that will be helpful for you also. Okay, so for the coding implementation. So here, quick sort, I'll also explain the that implementation which is given. So according to the conceptual things, so what is the concept for quick sort? So we have the one input list where some elements are given. Okay, some random elements are given. So like 2, 3, 8, 4, 5, 1, 6, like this. Okay. So according to the quick sort, we pick one pivot element. Okay, so pivot element is the any element we can pick. So generally we pick either the first element, we can also pick from the last element. Okay, and we can also pick the random element. So that if we are picking the random element as a pivot element, so that quick sort is actually called as a random quick sort. But here we are learning the basic quick sort algorithm. So here we are using first or last element as a pivot element. So suppose we are picking first element as a pivot element. So what is the meaning of pivot element? Here we are picking this first element. After that, we will process the complete list. Okay, we will process the complete list. We will check all the elements, and we will figure out that how many elements are smaller than this two element or greater than to this two elements. We will arrange the element by comparing to this selected pivot element. So after this process, so suppose if we process this like, okay, so after selecting this, we will just compare this 3. So 3 is a greater than this or smaller than this. Okay, if we are getting any smallest element with this, and what is our purpose here? We want to just shifted all smaller element of this 2 to left of this 2. Okay, and we want to shift all greater element compared to this 2 on the right side. Okay, smaller element on the left side and greater element on the right side. So this is our purpose. So in sorting algorithm, so after sorting, when you sort this list, so you will get 2 in some place, some position, and all element on this side will be smallest element, and all element this side will be the greater element. So that means this 2 is now on the correct place after sorting. If you can do this task, if you shift all the smaller element on the left side or greater element on the right side. Okay, so this 2 is actually come on the correct place after the sorting where it should come. So we are just doing this process after comparing the elements. So we are just performing these things. We are comparing 3, and after this is greater, so we will not do anything. So 8 is also greater, we will not do anything. 4 is also greater, 5 is also greater. Now 1 is smallest. Then at any time when we found any that greater element, so in that case, what we will do, we will shift. We will just swap this position. So what we will not this position. Okay, so we will swap this. Okay, so this one should become this side. Yeah, okay. So what we will do, we will just increment one counter in this side at the 3, because we found one element which is smaller than this. Okay, so we will shift one counter here, and we will swap the element with this element. Okay, so 1 and this 3 will come here. Okay, so 3 will come here, 1 will come here. Okay, so in this things, we will process further. So 6 is not smaller than this 2. Okay, no problem. And after completion of this process, what is the last point which we have got shifted? Okay, so this is this point at one place. Now we will perform swapping on this element. Okay, so 2 and 1. So in this case, you will get 1 here and this 2 here, second position. Now remaining will same 8, 4, 5, and 3 and 4. So now this element have shifted at the correct place, so where it should come after sorting, and all elements on the left side are smaller, all elements on right side are the greater elements. Okay, so this is the one process we are performing, and this is the linear process. Okay, so this should be performed in linear time with the complexity big O n. Okay, after one process, and that process actually called as a partition process. So this part called as a partition process. And after getting this 2 on the correct place, what we will do, we will call the same algorithms on the right part, on the left part. Okay, so we will apply quick sort on the right and quick sort on the left, and the same process will happen again. So same things, we will select the first element, pivot element here, and we will start comparison from the same partition. We will perform the partition process on this side, and in the same way this 8 will come at the correct place. All elements on the left side will be smaller, and all element on the right side will be greater. Then again we will perform the quick sort on the left or right part. So this is the process for this. Okay, and what implementation is given, let discuss. So let me open that. So here in notes, I've given 2 implementation. Have you checked these 2 implementation, or you have checked only the lecture implementation? Okay, I'm not getting. Okay, so here let me explain this implementation where the partition function is defined separately. Okay, and for this part, okay, this is the partition process, this is the quick sort algorithm. Inside the quick sort algorithm, what we are passing a list, lower index, upper index. Okay, lower 0 or upper index, what we have. If lower is less than upper, this condition we are taking. If this condition is true, then we are calling this partition process on the list with lower index and upper index. Okay, and this partition process will perform the same task. It will just select if first element is a pivot element, it will shift all smaller element to the left, all element bigger element to the right, and after this process it will return a correct position of the pivot element where that pivot element is coming after the process. Okay, that position it will return, that will come inside the for the pivot position. After getting that position, so that means we got the position for 2. Okay, so that index is 0 1, and here 1, and here the remaining element 2 3 4 5 6, so like this, or elements greater than this. So this partition function will return this index 1. Okay, so that means nothing to do with this element, this have already shifted at correct place. What we will do, we will just call the quicksort algorithm on the left side or on the right side, but we will not touch this. So here we are doing the same things, quicksort. Okay, so L lower this index, what is the lower index we have, and pivot position -1. Okay, so the pivot position is 1, that means -1, that means 0. So what is the lowest index and the one index before this pivot element? Okay, that part we will call the same quicksort algorithm. Okay, recursively, and right part. Okay, so this is the right part, L pivot position +1, so that means from this 2 index to last index, so this is the upper index. Okay, so this recursively actually performing on the same left or right side, and the performing the same task every time. In the pivot process, you can see we are selecting the pivot element as the lowest, that first index element. Okay, so this lower is representing the first index of the list. Okay, and then this is the value, pivot value. Okay, and this is the index for that. Okay, I is equal to lower means index, and L lower means value. After that, we are just traversing all the elements by this one single loop for j in range lower +1 to upper +1. So this is the range, so that means till upper. And every time we are comparing, if Lj is less than equal to pivot element, okay, then we are shifting our I one position ahead and performing swapping. Okay, with the that pivot position, this j position. So at any point, if we are getting a smaller element compared to the pivot element, we are increasing our I position one position ahead and then performing swapping. Okay, in that way we will perform this type of swapping, and in last, after completion of this loop, where we have reached, so this, what is the I value we have reached, so this is the I value, we will swap this I position element with the lower element. So this is the actually pivot element, okay, so which we have selected as a pivot. So we will perform this swapping. So pivot element will come at the correct place. All element on the left side will be on the left side, but there is no guarantee that all elements are on the left side, that is actually in sorted order or not. Okay, so it may be in any order, but all elements are smaller than this. All elements are on the right side actually are the greater element compared to this lower. And finally we are returning this I index.
Sir, if I may ask this, so here first actually there is a for loop, and inside that there is a if, right?
Yes.
So it is why we are saying it should be n square, right? Why we are saying big O n, the
No,
time complexity?
So this is a constant operation. This is one condition only. Here, this J loop is running like J equal to 1 to n. Okay, because we are starting with lower plus 1, so we are not taking this with n minus 1. Sorry, indexing we are taking. So we are not using 0 index. We are starting from 1 to n minus 1. Okay, so this is approx n. But for every value of J, this is constant condition. All are constant condition. This is not a loop. So this is not a loop. This is a conditional statement that will only take constant time.
Okay.
Okay. So this instruction will take constant time. This instruction will take constant time. This instruction will constant. This will take constant. Total 4 constant time. So we will consider as a big O1 complexity for this part.
So, and one more doubt, this after once it is called, right? Let's say we are calling any of this function once, then it will not be completely shorted, right? It will just
yeah, one element is actually
one element will be getting in the right place.
So what happening, yeah, for this complexity calculation, we will just check. So this function, okay, just consider this function. What is the complexity for this function? Order of n?
Right.
Correct. And this is a recursive function. This is a recursive function where we are calling the same function on the half part. Okay, if we can consider that our pivot element is coming always in between, so that means our list is dividing into the half part every time, and we are calling the quicksort on the each half, both half. Okay, so how we can just draw the complexity for this? So initially, first thing, how we can write the recurrence relation for this? So Tn, okay, Tn is the total time for n input. But to calculate this, our algorithm is calling the same that same function on the half of the input 2 times. So that means we have to figure out that what is the complexity for this part and this recursive part. Okay, so these are the 2 parts where the input is actually half. So we can write like this. So T, what is the time for the same complexity, the same algorithm with the input n by 2. Okay, so Tn is equal to this Tn by 2. So what is the time for this? And we have 2 call. Okay, so we will write 2t. So one is this call, and this is the second call. So 2 times Tn by 2, we are calling the same function. Apart from that, we have this one partition function called from this function. Okay, so what is the complexity for this partition function? This is big O n. So this part is actually written as a how much time we are calling the same function and what is the input. Okay, so this 2 is actually representing number of recursive calls. This is for each recursive call what input we are passing, what is the size of input we are passing. So this is the recursive part. Apart from the recursive part, what are the time complexity for other part? Okay, so this is order of n. So this is called as a recurrence relation for this quicksort. Okay, and here we are considering that if we are getting pivot element, we are getting in, so after partition process, our pivot element is coming in between. Okay, so we are considering this condition for this quicksort algorithm. So this recurrence relation is for best case or average case, we can say. So what would be the complexity after calculating this Tn? And you have already seen this type of recurrence relation for merge sort also. Okay, so same recurrence relation we have for the merge sort. So Tn, you have the initial part, and so what is the okay, so after that we are calling Tny2 Tny2 plus this n. Okay, so that means apart from this two recursive call, we have another time is n. We are writing here. Okay, now this is a new problem. Consider that this is a new problem where the size is n by 2. So how we can further explore this? So that means again this algorithm will call two times recursive call. So that is actually Tn by 4. Okay, and Tn by 4 here. Same, this is a separate problem. This again will call two times Tn by 4 and Tn by 4. So we are exploring the same equation, recurrence relation. And apart from this part, Tn by 4 plus Tn by 4, what is the additional time is required for the partition process? So in the above case, it is taking order of n when the input is n. But here input is n by 2. Okay, so it will take n by 2 time here. Okay, n by 2 for this part. Okay, so for this part n by 2, same here, so plus n by 2. So that means two recursive call and n by 2 additional time for partition process, two recursive call and n by 2 time for the partition process. If you add this n by 2 and n by 2, this is the time for partition process, you will get complete n time. Okay, on this level.
Sir, why are we getting, sir, here I did not understand one point, sir. N by 2, why are we getting, sir?
Yeah, we are using this recurrence relation. No? So inside this function Tn, we are calling the same quicksort algorithm two times inside this. Okay, so we have written 2t and we have passed half of the size. Okay, after partition process, we have passed n by 2 elements on the each part. So we are, that means we can write like this Tn by 2 and plus Tn by 2.
Yes, sir.
Plus big O n like this. Okay, so we have just considered that 2Tn by 2. Now we are exploring this equation only. So if we have Tn, so that is divided into two recursive call. Okay, Tn by 2, Tn by 2. And apart from that, we have this time, n time for partition process. Now just consider that this function. Okay, so if you explore this Tn by 2, just replace this n with n by 2 in the complete equation. Okay, so now this Tn by 2 will be considered as 2t. Now n by 2. So here input is n by 2. So n by 2 divided by 2. So that will become n by 4. Okay. And at the place of n, we are passing n by 2. So here will come big O or not big O. We generally write the time for here. So n by 2. Okay. So here we are calculating the number of operations. So we will not use the complexity for here, but we are exploring this. So you can see for this Tn by 2, we have written Tn by 4 one time, then second time Tn by 4, then plus n by 2 time for this part. Okay, this part. Now similarly for this part, this is again recursive call. This will explore, this will expand again. Okay, so Tn by 4, Tn by 4, and then n by 2. If you add all the number of operation at this level, so n by 2 from this, n by 2 from this. So total number of operation at this level is n. Okay, if we expand one more time, so this Tn by 4 will again divide into two call. So that is Tn by 8. Okay, plus Tn by 8, and plus what is the partition time? That is n. That is n by 4. Okay, n by 4. Now second this one. Okay, so this will again divide into two. So Tn by 8, Tn by 8 plus n by 4. Okay, so this is for 2, same for here, same for here. So total 4 times. Okay, so this is 1, 2, and 1 from this side and 1 for this side. So you will get at this level 4 into n by 4 total number of operation for partition. Okay, so 4, 4, and again you are getting n. Okay, so in that case, how many levels will be there? That is actually log n. Okay, so every time we are dividing the size n by 2. Okay, so that means n by 2, then n by 4, then n by 8. In that way, we will reach to 1 in log n steps. So that means each level total number of operation are n, and we have total log n levels. So total number of steps will become n log n for this complexity. Okay, so this is the complexity for best case and average case. But what is the worst case situation for quicksort we have? So suppose if our pivot element is not coming on the middle part after the process, it is coming on the one corner side. Suppose we have a list like this, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, suppose this is the input list. This is already sorted. But still, if we apply the quick sort process on this, so what it will do, it will take this, it will select this element as a pivot element 1. After that, it will process the all elements, but all are greater than this. Okay, so that means after performing partition process order of n time, we will get this element position as a pivot position. So that means it is coming at the first place, and remaining elements we have on the right side. No left side is there. Okay, so that means 2, 3, 4, 5, 6, 7, 8, 9. We all these elements will come on the right side. So quick sort will apply on this part, right part. Okay. Again, same things. This is the pivot element, but after the complete process, we will get the same position for this, and we 3, 4, 5, 6, 7, 8, 9 will come on the right side. So n time partition process is applied here. Okay, and every time we are getting the our pivot element on corners for first place or corner place, and we are performing the same task on the n-1 element again. Okay, so that means next steps when we apply the quick sort on this, n-1 steps are required. In this step, n-2 steps are required. Okay, so in this way we are just reducing one element at each recursive call, and n-3 like this and 1. So we are getting the series of the operation like this. So n plus n-1 plus n-2 plus n-3 like this. And if you add this series, you will get the like this operation. So n into n plus 1 divided by 2. Similar to your insertion sort. If you have done insertion sort, okay. So this is the similar. So you will get the n square complexity. And what will be the recurrence relation for this? Tn equal to, and recursive call is performing on the right side element, okay, which is 1 less than. So we can say that the time of n-1 and plus big O of n for partition process. So here our elements are not divided into two equal part. Okay, here we are calling our quicksort only on the right part every time. So and that right part contain n-1 elements. So because of that, we are getting this type of recurrence relation. So Tn equal to Tn-1. And if you expand this equation, you will get this type of series, n-1, n-2, n-3 until 1. And for this series, we have the addition formula, and if you add this n into n square, this is the highest order. So overall complexity will become order of n square. Okay, so this is the worst case situation for the quick sort. If input is either in sorted order 1, 2, 3, 4 like this, or input is in reverse order, so 9, 8, 7 like this till 1. If you are selecting first element as a pivot element or last element as a pivot element, okay, so these both cases are actually a worst case for the quick sort. So in both cases, it will take order of n square time. But other case, for best case or average case, we generally consider that our pivot element is not coming in the corner after the process. It is coming in between. So in that case, our complexity will become n log n. So these both cases are written here. So best case, this is the recurrence, and worst case, this is the recurrence, where our pivot element is coming on the one corner side. Okay, so we are getting order of n square. So yeah, this is all about the quick sort implementation. So any query in the code implementation, code understanding?
No, sir.
Yeah, so the best way to understand the code is only just apply a one or two dry run. Okay, just take some small input and apply the dry run. Just pass the input by paper and pen, not on the computer. Okay, just apply the one dry run on the code and just check what happening actually in the code. Okay.
Sir, that example you gave, that list, right? With that, if we want to understand, while calling this, what should be my lower value and upper value here? You gave na 2, 3, 8, 4, 5, 1, 6.
This lower and upper you are asking?
Yeah. So when you are calling the
These are the index. These are the index for the algorithms.
okay, sir, we are calling this quick shot, right? We are calling the quick shot, right? When we are calling this, we are passing one list and lower and upper. So what is this lower and upper here?
The lower upper is 0 for the list.
Uh-huh.
What is the smallest index for the list? 0.
0.
Upper is the last index.
Okay. Okay. So we have to tell, right? We have to tell when we are calling, because
okay, so input, that input part is not mentioned here, but according to the algorithm, so this is actually index. Same things we have already seen in the binary search, where we don't, if we don't want to use the slicing things, that we pass the index of the algorithm. So what is the actually first or last index, and based on that we divide actually the list. So here we are performing our sorting on the same list. That means this quick sort is performing on the same input list. It is not using any additional list in the code.
okay.
So this is in place algorithm.
So instead of calling that way, we can just tell at the lower L dot L of 0 and L of length of L minus 1. Like that we can call, right? I mean,
yes.
Okay.
So let me just run this code. 1 second. Yeah.
Sir, the partition function, the last step I didn't get, sir.
So let me just run this and I'll explain. Okay, so this is the algorithm, and let me call this function. So we are creating one list. We are passing some element like 4, 3, 6, 2, 8, 7, 1, 9. And after that, we are calling this function. So quick sort is calling on this L, and we will pass the index 0. And what is the last index for this list? 1, 2, 3, 4, 5, 6, 7, 8. That means 7. Okay, and we will print the output. So print the return value of this function. Okay, so we are calling like this. So if we run this, you can see we are getting the correct output. Correct. So let me explain. Okay, I have also mentioned the Python tutor for this in the code. Okay, here, yeah. Okay, so you can just check the code implementation with this help of this Python tutor. Okay, how it is working. So you can see how we are calling this function inside this. And after that, each steps you can see how this is working. So like first time we have called this function. So this is defined. Yeah, so this is the list defined first. After that, you can see L is defined with this element, and then we call this function. Now our cursor is moved to the function and enter into the function. And here you can see we are calling the partition process. So it will jump to the partition function from here. And you can also check what is the lower value and upper value at this situation. So lower is 0 and upper is 6. Now next steps, you can see we have jumped to the partition process. Now inside the partition process, this lower and upper is a separate variable. Okay, this is new variable for this partition process, local variable. Now here the value is lower is 0, upper is 6. Okay, now we have taken this pivot is the first value. So this is actually 4. What is the value for at 0 index? This is as a pivot value. And what is the index for this? So that we have taken for I. So now you can see we have got I equal to 0. And inside this loop, we are running this lower plus 1. So that means lower plus 1 is 0 plus 1, 1, 2. And this is not included in the range. Okay. So upper plus 1. So upper is 6. 6 plus 1 is 7. But our index will move till 6. Okay. So that means 1 to 6 we will process the element. And each time we are comparing this LJ element. Okay. So LJ is reading the value L1 is less than pivot element. So this, okay, 3 is less than pivot element. Yes, correct. This condition is true. Now we will enter inside this. So we will increment our I. You can see I will increment here. So you can see 1. And after that, we are simply performing swapping operation between this 3 and this 4, I and J value. So we are performing swapping. Okay, so this 3 is a smaller element. That means we are performing swapping. So this 3 will come here and 4 will shift to the right. Okay, so now next iteration, same things. Now we will compare with the 5. So 5 is greater than the pivot? No. Okay, so Li, Lj. Okay, so the previous step. 4, 3. Okay, so Li. Okay, I is lower, Ij, or J was 1. So 0 and 1. 0, 1, and it is swapped or not? I plus. Okay. So I was lower. Okay. And I we have increased to 1 and J was also 1. So 1, 1, this swapping is not performing because both are I and J are indicating to same element 3. So, but we have moved our I and we will decide this I is actually deciding the pivot final position. Okay, if any element which we are finding is smaller than this pivot element, we are shifting our I to the one position right. Okay, so that means we are figuring out the correct position for the I value or that pivot value. So this is the first iteration. Then second iteration, we will check. So this condition is not true because this 5 is not less than 4. So we will not do anything. Once again, repeat. Now our J is 3. Okay, and again J is 3 means 5. Have we done? Okay. Okay, so we are also doing this swapping. 1 second, this is outside. Okay, it's a little bit confusion. Let me run again. So this is now going enter and swapping is performing with the same element. Nothing is happening. So now we are going. Okay, if this condition is not true, then we are directly moving right. 5 is less than 7. Okay. This is swapped. I will run this for 1 second. Go next. Okay, so here from this side. So okay, pivot is lower, pivot is the 4, I is 0, J is 1 now, and okay, so L1 element is 1 is 3. 3 is smaller than this 4. Yes, and we will increment our I to 1 position, and then Lij, no swapping is happening. Now we are moving J equal to 3. No, J equal to 2. So 2 index element is 5, and this 5 is not less than to the if condition. This condition is not true, and we will repeat back. Okay, yeah. So we are moving 1 position J equal to 3. So this 2 is smaller than 2, 4. Correct. Okay. So in that case, we will just move our I 1 position ahead. So I was previously 1. It will move to the 2 this position, and we will perform swapping between 2 and 5. Okay. So 2 and 5 we will perform swapping here. So you can see both are swapped, and then now our I is pointing to this 2 position. Okay, and our J is moved to this 4. This is 6. 6 is not less than 4, so nothing will happen here. Okay, Now j is moved to 5, so 1 is smaller than the 4, correct? Okay, so now we will increment our I to 2 to 3, that means 5, and our element will swap with this. Okay, so 1 to 5. So here this will performing swapping, so you can see 1 and 5 are swapped. Okay, now we will check 8. 8 is not less than 4, so nothing will happen. Okay, now loop is completed. So we will come back. So where is our I actually? So I is pointing to this position 3. This is representing that all elements from this to this pivot element, okay, that is actually smaller than this pivot element. Okay, so this 3 to 1, all elements are pivot element. Sorry, smaller element to this first 4 element. Then we will perform swapping between 4 and this I value, 4 and 1. So this is the last swapping operation here. So you can see after this 4 is moved to here. Okay, and this is the last step. Now 4 is shifted to the correct place where it should come after the sorting. All elements which are coming before this, that are actually smaller, and all elements which are on the right, that all elements are on the these are elements which is greater than this. So now return I. So what is the I index we have? 3 index will return to the that partition function. So you can see return value 3. Okay, by this function. So this 3 value is coming to this pivot position here in this code, and our algorithm will call again on the left or right part. Okay, so from this function, actually this function is called again, and new partition process is generated for 0 to 2. Only this part, this is the left part, the same algorithm again called again. Okay, you can see L, lower is 0 and upper is 2. And after this process, it will complete, the same things will perform on the right side. So in this way, this code is working actually. So you can just run the code step by step and see what value you are updating in the data structures which is used in the code.
Sir, after the first iteration, now the current state, right? One is at the 0th index. Now, when it will call next time, should it consider 1 or it will go from the index 1?
No, for the next iteration. So after first iteration, we have received this position correct for okay. So this will not touch this part. 0 to 2 list will be called quicksort will be called on this part 0 to 2 index. Okay, and this 1 will be select the pivot for that. Okay, same algorithm we will same process we will apply on this left part of the list. This part 0 to 2. Same process we will apply on the right part 6 this 6 5 8, where the lower index will be considered as a 4, upper index will be considered as a 6. So this will be passed to the next recursive call. The same process will apply separately. Actually, this is new problem again. So same first element will be considered as a pivot element again, and then we'll divided in the list into the next part. So in this way, list will be sorted. So every time pivot element will shift it to the correct place. So and list will be sorted in the final. Okay. Yeah, is it clear concept?
So, sir, that maybe it is very silly what I'm going to ask. The list size, even or odd, it will not matter, right? Because
not matter, yeah.
Yeah, first element, which is our pivot element, that is after the first iteration, it is getting into the right place, and so we are taking the first half and the second half, and then doing the same thing in repetition, right?
Yes. So it doesn't matter what size we are getting on the left or right.
Yeah. Okay.
We are just passing the same quicksort algorithm on the left part. If suppose left part have only 2 elements, right part have 6 elements, so that will work as a new problem.
Okay.
Quicksort will work separately on the same part. Okay. Okay, so it is fine. Quicksort. Any other query in this? Okay, so you can just apply 1 or 2 dry run on the simple some like worst case or best case. Okay, You can take the example for both type of input. So like suppose if you pass the value, we have to edit the code. What is the worst case situation we have actually for this? So let me take this type of input. 1, 2, 3, 4, 5, 6, 7. Okay. So in this case, so 1, 2, 3, 4, 5, 6, 7. Oh, okay, input size is okay. So now visualize this, and you can see how we are getting the element. So this is the first call. We have total n element, and we are calling this partition process of all n elements. Okay. So after this complete process, you can see return value is 0. So that means what is the pivot element position, which is 1, we are getting 0. That will remain on the same position. And this quick sort algorithms, this first part, okay, will be applicable on index from 1 to 6. So you can see what is the lower and what is the pivot position -1. So what value are passing. So you can see lower equal to 0 and upper equal to -1. So -1 is also represent the same last index. Okay, so in the Python, this -1 is also represent the that last index. Okay, this we got actually because of this pivot position -1. So 0 -1 is -1. So this is representing the upper bound, this 6. Okay. Then that means we have now called the quicksort on this part. So same things we will perform again, and now okay, so partition process will complete. So no condition is satisfied, and then we will return from here 1. So that means the next iteration, this position is returned, and the algorithm will call on this part. So lower value will be 2 and upper value will be -1. So yeah, upper here is calculated 6. So lower is now 1. Okay, this is not called right now. Yeah, this one is 1. Lower is 1. So I think something is wrong in this code. Okay, so this part is actually not calling because yeah, this part is actually calling. Okay, so fine. So lower, actually this part we are not getting any left part, so this function is not calling. But yes, second function will call with this index. So 2 to 6, you can see 2 to 6. This part is called. So in this way, 3 to 6. Next, this is the next call. Then 4 to 6. This is the next recursive call. Then 5 to 6. This is the next recursive call. But so you can see how many times we are calling the same function. So this is working like I say n, n-1, n-2, n-3. So this is the worst case situation for the quick sort. Okay. So now this is quick sort. Let's move to the linked list part. Okay. So I think linked list is the also a difficult topic. So any specific query anyone have in the linked list to understand? Okay, so first thing we will understand that what is linked list and why this is useful. So in Python, actually we have some dynamic data structure like this list. This list have we can increase the size at the runtime. We can append any number of elements at the runtime also, and that list will increase. But in the previous language like C, when we use the array, actually, so array is called as a static type data structure. Static memory allocation happen. Okay, so if we can assign the size like for the array is 10, so that means at the runtime we can only use the 10 size. Okay, so for array, if we for the at the run compile time, we have to actually initialize the size for the array, and that we cannot change later at the runtime. Okay, So this array was actually a static that memory allocation. So, but in Python, this list can be increased or decreased at the runtime. So this will not come. We cannot compare this list with array. Okay, so array have some limitation, but this linked list actually developed with some advantage of the over the array actually, where we can increase the size, or we can store, we can assign the size at the runtime with the help of some dynamic memory functions in C language. Okay, where we use some memory allocation at the runtime using malloc, calloc, some dynamic function. But same concept here, we are learning linked list. This is called as a dynamic data structure. We can create a memory allocation at the runtime when our code is running, and we can store the data. Okay, and this is not required here that the memory will allocate continuously. Like as array, if we allocated 10 elements, so all 10 elements actually allocated at the continue memory location. So suppose if first element is allocated like this 2020 memory location. So suppose if one element, we are assigning this array for integer, and integer take 4 bytes. So next element will consider as at the address of 2024. Okay, this address. Next element will come at the 2028. Okay, in this way, continuous memory allocated for the array. But this is not the case of linked list. What we can do, as per the requirement of the data, what data is coming at the runtime, we at that time we can allocate the memory and we can store our data. Okay, if we have only one element at the runtime, we will only create the space for one element in the memory, and we will store this one data in our memory in some place. So suppose this size is actually 2020, this element, and suppose if we are getting one more element to store at the runtime, we will create another memory allocation for that, and the size is not required to continuous. It may be anywhere in the memory. Okay, so like this is 40450. Okay, and we will store our second element in this space. So second element like this 2. Okay, but we will link our element in some way, so later if required we can access the element with the help of this linking things. Okay, so to link this element, what we will do, we will store the address of second element. So what is this address of second element with this first element? Okay, so this first element is stored at this location. So we will create a memory for some extra memory, some part for data and some part for the address of next element. Okay, so this second part actually we will store the address of next element if we are storing. Okay, so this 4050, this will we will store here. So 4050. Okay, so logically this is linked actually. Okay, so if we are reaching at this position 2020, so we can read the data and we can also read the address of the next element. So this is 4015. So directly we can jump to this location, and same things, we can read the data and we can read the address of next element. So in this way, all elements will be linked by the address. Okay, so we will store the address of next element to the previous data location. Okay, if we know the address of first element, we can traverse all the elements. From first element, we will read the address of second element. From second element, we will read the address of third element. And in that way, we can traverse all the elements on different memory location. So there is no need to allocate continuous memory allocation here, and that memory allocate from anywhere in the memory, but we will logically link these memory locations and later we can access all the elements. So that things actually we are trying to do here, the linked list concept. Okay, so link, according to this name, this is a list of elements, and this list of elements are linked by the address. And so this is the formal things for regarding this linked list. There are two types of linked list: singly linked list and doubly linked list. And in this linked list, we have one single node or pointer, we can say that, or variable, anything. This is generally we call as a head or first. We can give any name. Okay, so this is just a variable. but this store the address of first element, okay, or reference of the first element. After that, the remaining element address will be stored with the same data elements. Okay, so there is one variable or pointer for the first element, and after that, each node, we are generally called this as a node. This is just a memory location space. This node contains two fields, one for data and another for next. Next is just a reference area for the address. So this head is containing only the address of first element, and the first element containing the data and the same field. Okay, so we have allocated the some space where the one is part of that space is actually storing data, another part will store the address of next element, okay, or reference of next element, and same things we will repeat again. So this is 20 and the reference of third element in this way. So during the storing the data, at the time of storing the data, we will just maintain this linking. Okay, so suppose if we want to store one more data, 40, we want to store 40 in this list, and this is already done. So what we will do, we will allocate memory space, and so any address we will get for this, so 40 will store here, and we will just pass this address. So any address we are getting, we will pass at this place. Okay, so this will remove, and we will store the none value with the last node address field. Okay, so because this is just an identification, there is no element after that. Okay, so now this is linked logically. So 30, after that we can read the address of 40, and we will move to the 40, and after that we are reading the address, none, that is none, that means nothing is after that. So in that way, at the time of store the data, we can maintain this linking address, and later we can access the element by the help of this address traversal.
So this default list in Python, how they are stored data, they will be homogeneous, like in same.
No, the list is not homogeneous. This Python list is not homogeneous. Okay, you can experiment this. Python list can contain any type of data, heterogeneous
No,
data.
I mean to say how it is occupying.
So what
space in
happened
memory.
actually when you store, so this is allocated by default memory, some memory allocation. So like if you create one list like this, okay, so some element storage that actually provided, like for 4 element or 8 element, like this continuous memory location, it will provide to you. Okay, so suppose if you are storing one data and then 2, then 3, and 1, 2, 3, 4, and this is exceeded. If you increase one more data, next again some batch, some size will be allocated to you again, 4 byte like this. Okay, so if you are storing one data, that means at the initial, or if you are just initializing this list, 4 element, suppose 4 element space will be allocated to you. If you stored 5th element in this, again 4 element space will be allocated to you. Okay, so in this way, this is actually increased at the runtime also. So some fixed space is there that will allocate it if you are adding any new element. If your previous that block is full.
But basically, so, it is a continuous memory allocation.
So that not this is not guaranteed. Okay, so this first one block may be continuous, but if at the second time if another block is actually adding, so that is there is no guarantee that that block will be continuous from the first block, but that is actually will be linked. So that is memory is allocating, and every allocation is actually an object in the Python.
So
you have some reference for that.
So in this case, this is not a linked list. Which component in Python mapping this, keeping the link that this first portion is in?
So this is the internal things of the how the list is actually designed, how they are providing the mapping thing. Some mapping is there. So in indexing is also providing here. So because you know that in Python everything is an object. Okay, you have creating a list. This list is your object. If you are creating any variable, it is your object. If you are creating any space, so that L0 will also be referring to a one object. Okay, so in this way, memory will be allocated. After that, if you complete this, and if you want to add one more element, one more part will be allocated to you, and that will be actually maintained by some another implementation, that internal implementations. Okay, so there's no addition known component which is defined, which we know that how the Python list is actually internally implemented. But this is dynamic actually. This Python list is dynamic. You can increase the size at the runtime, you can decrease the size. This is not fixed like a array of the C language or C++, like this. Okay, so this Python list and this linked list is totally different concept. Okay, these both are not the same. Okay, so yeah, this linked list, this is the structure of the linked list which we have here. Okay, so this is the representation. Okay, this is for
Sir,
doubly.
why to use that linked list? If we have a default data structure list, why to go for a linked list?
Yeah, because we actually got some advantage of the linked list to implement some other data structure. Like suppose if you want to implement that queue data structure, you know queue operation.
Yeah, yes.
How the queue is actually works. So in queue, you will always insert the element from the last. Okay, but at the time of remove element, you can only remove from the first. Correct. So this is the queue definition. First in, last out. FIF. First in, F below, or last in, first out, like this. We can see that. Okay. No, last in, first out. This is not. This is for a stack.
First in, last out.
Now, first in. No, first in, first out. Sorry.
FIFO, yeah.
Yeah, first in, first out. Yeah, this is the property of the queue data structure. Those data are inserting first, that will remove first. Okay. So similar like a general real life scenario, if you are entering into any physical queue, so those who are coming first will work first, like we consider as a first. So same things, if we want to perform this quick that queue implementation, if we want to implement the queue with the help of some data structure, so suppose if you want to implement this with the help of list, Python list. Okay, Python list I am talking about. At this time, what will happen? So this insertion operation from the end, what will be the time complexity for this? If you want to implement, and this Python list also have indexing 0, 1, 2, 3, 4, like this. Okay, and if you want to implement this with the help of Python list, and you want to add one more element in this at the end, so what will be the complexity for this operation? Constant. Okay, so you will append, like if you have L list, L equal to, you simply use L dot append. Okay, and some element like 3, 5, any element. So that will append n to the last. So that will not impact the index of any other element. So this is only single operation, and one new element will be added. So this is constant operation. But if you want to remove one element from the list, so in that case, if you want to remove this element from the list, so that means after removing this, all element indexing should be shifted one position to the left side. Okay, so this one should be come at the 0 index, like this. Okay, so that means this removing the element from the list, that is the first element. If you want to remove the first element from the list, so all element will be shifted one position to the left. So in this way, this operation will become order of n operation, not the constant operation. But same things, if we implement this operation, this queue things with the help of linked list, so you can maintain what you can maintain. You can maintain head. Okay, that is contain the address of first element, and you can add all element in this list. Okay, and you can also maintain one tail pointer that will contain the address of last element. Okay, so in this way you can implement the queue where the both operation can be performed in the constant time. So what you can do, you can perform insertion at the last. Okay, so insertion at the last, tail, but tail always contain the address of last node. You just need to create one memory allocation and just add the address of the last element to the new added element, and just shift this tail to this element. Okay, so this 2-3 operation are required. That is actually constant. And same time, you can also remove the first element from the first position from the linked list, and you need to perform only one operation. Just shift this head pointer to the next element here. Just store the address of next element to this head variable, and this will be removed. So this is also a constant operation. Okay, so both operation you can perform in constant time. One. So this will work as a fast queue operation. Okay, so this will improve the complexity. So sometimes some implementation this linked list is helpful, and you will see some like some polynomial expression you can solve with the help of this linked list. Some example is there, but not too much, because in Python language we can do all the things with the help of another data structure like this linked list things. Otherwise, this linked list is very helpful in the other language like C. This is dynamic data structure, so you can store the data dynamically, and you can store the any number of elements, and you can decide the size at the runtime. But this is also helpful for some other data structure implementation. Okay, but and you will also see the some implementation like this tree implementation with the help of the similar type of logic. Okay, so you will create some memory allocation for the one node, and you can add the node like this. Okay.
What is that other data implementation you are referring to that we can achieve linked list?
Not the exact same structure, but yeah, you can implement tree data structure. Okay, so tree data structure where you can store the data like this. So 3 space you can allocate, and inside the 3 element, one element you can store the data. This is the left child address, and this is the right child address. Okay, and logically you can note the elements in the tree. Like, okay, so similar type. This is the similar type, but here we are storing the left child address and right child address, and same things we can repeat with the next node element, and we can store the data in the tree form with the help of same concept. Okay.
Okay.
Yeah, so this is the concept how we are just linking the nodes. So in Python actually we have implemented this linked list with the help of class. Okay, we have just created a object of the class, and we are linking in the similar way, because here in Python there is no memory address things. In C actually we implemented with the help of this memory address, this malloc, calloc, and this pointer thing. But here actually there is no pointer concept, so we are implementing these things with the help of this class object things. Okay, so regarding so this is the singly linked list. What is the meaning of singly linked list? It's actually where each node only contain the address of next node. Okay, so there is no way if you are moving from first to last side in this list, you cannot back to the previous. Okay, because here each node contain only the address of next node, not the previous node. If you are at this position, this 30, you cannot move to this 20 because this node not contain the address of previous element. Okay, you can only move to the right side. Okay, to next till the last. Okay, and so in this way, this is based on the problem, we can decide that how many pointer we can take for this. So head we can maintain. Sometimes we can also add the tail pointer, so that tail will always contain the reference of the last element. So that will actually improve our some efficiency for the sum operation. So based on the problem, we will decide that so head or tail, what is the required things. But this is the singly linked list where we are maintaining the address of next element only. In doubly linked list, the concept is same, but in each node we are containing the address of next element and the previous element. Okay, if previous element is not there or next element is not there, we will store the none. None means nothing. So here you can see we are allocating some memory space where 3 fields we are maintaining, one for data and another field is for next address of next element, and address of previous element. So if we are maintaining our data in this way, we can traverse the list in both directions. Okay, we can traverse from head to this right side, and at any point we can also traverse from right to left. Okay, because we have the address of both sides. So This is the another representation of doubly linked list. So we can also design this. So regarding this implementation, so professor have used the recursive implementation for the same class. Okay, and if this is not clear, that another implementation we have added that is actually contain the separate two class. Okay, so this is recursive implementation. What we are doing, if you know that we have created one class node. Okay, inside this node class, we have taken one variable b, and we can create the object and we can pass the value of this b. If this is not passed, this is by default none. Okay, and we have, you can see what field we are taking for the node. So that is, one is value, another is next. So value means data and next means reference of the next node. Okay, so this is the actually a constructor that if we create any object for this node, so by default this two field will be created for that. And these are some function which we can use to perform some other things. So like append element or that append. This is recursive implementation. Okay, and this is iterative implementation. And insert and any position, insert new element, delete element. So these are some operations recursively which we can perform. So what happening actually? So if you are creating any object for this, okay, this function, so like this, we are calling head node 10. Okay, so this is the first call, and this is simple variable, first variable, and one object is creating for the same class node here, and 10 values is storing. So what is happening actually? This head pointer we have, pointer or reference we can say that, and we are creating a object. That object contain two field. One is value, that value we are passing here. This is 10, and another is none. Okay, so that address of next field. But at this point, we are not passing what is the next value. So this will be add like as a none. Okay, according to the definition, you can see this is the first definition, none. Okay, so by default this is assigned to next none when we're creating the object. Okay, and after that what happening? Head dot append 10. So this is the effect of first call. Okay, when we created the first object of head. But after that we are performing the other operation on the same object. We are not creating any other object, but recursively we will create the new object. But you can see head dot append. So that means we are performing with the same object. So this head is a object for the class node, and inside this object we have some function that is defined for this object, that is actually append. So append is like a one new element will be added into the last. So you can see this v is the value of the new element, and what we are checking inside this function. So if current node is empty, okay, so current node is empty means if this v is not passed in the first stage, and this v will also be assigned this value equal to none. Okay, so this is the case if we create the object like this. So head equal to node only this. Okay, so if we create the head object like this, so that means no value is assigned to head this first place. So this will become empty node, none here and none here. Okay, but in this case we have just created the object with the value, so that value is also assigned. But we will check the both condition if value is assigned to or not. Okay, so this first condition is just check if self dot is empty or not. So is empty function is also defined someplace. So that is empty function. If self dot value equal to none, that means the head actually contain the none value or not. So if this is true, then we will store the data self dot value equal to v. That means we will store the value in the first place in the same here. Okay, if this is not none, then we will create a new object. So you can see we will recursively call the, we are creating the object, not recursive here. Yeah, recursive is there. Okay, yeah. So here, if this condition is not true, this is not empty, then we are checking the another condition, self dot next equal to none. Okay, so that means we have only one element in the list. Okay, and then what we will do, we will self dot next equal to node. So this is the another, we are creating the object for the same class node. Okay, so this is object we are creating and we are passing the value. So by default, what happening when we are calling head dot append 20? Okay, so what we are writing here, so head dot next, so head dot next inside the append function, head dot next, this next is pointing to this location, equal to node and 20. So this is called inside the append function. So node will create a new object here, and this 20 will assign here, and by default this none will assign here, and this reference of this node will be assigned inside this location. So this location will be linked like this. Okay, so the reference is assigned to this head.next here. So this is now linked. Okay, now next thing, again we are calling same things, head.append 30.
Sir, can you repeat that part again?
So actually after creating a first object, so this node 10, so this part is created. Okay, one node is created with the value 10, and this is none. But when we are calling the append function from this object head, so that means inside this function we will just check if we have first element and the next part is none. Okay, if this part is none, then we will add the new object and we will store the address or reference at this place. So you can see in the append function, so if the first node is not empty, then we will check if self.next, that means if address is equal to none, that means no element is after that. So we will assign self.next equal to new object we will create here with the value v. This v is actually new value which we are inserting, 20. Okay, so new node will create for the by the same class. Okay, same things, and that node will be logically created like this. 20 will allocate it, and the reference of this node will be assigned to this next field, this previous next field. Okay, so in this way now two nodes are linked, two objects are linked actually. Okay, now again we are calling head.append 30. Same things, we will start from the check first position, head.10. This node is now contain the elements. Now we will check the next field is none or not, but here this is not none because this is containing the reference of 20. So this is the next condition. You can see first condition is not true, second condition is not true, then we are moving to self.next.append. You can see this is a recursive function, same append function we are calling to the next node, next object. So self.next.append, that means we have changed the object, we have jumped to this node and calling the append function from this node, and same append function will call here, and it will check this is empty or not. No, this is not empty. This next field is empty, that it is contained none. Yes, it is contained none. So we will write like this. So the next equal to node 30. Okay, so one node, new node will create, and 30 will store here, and the reference of this will store at this position. Okay, so this none will be removed. So this way, next same things, head.append 40i. So this is iterative process. So here recursive call we are not doing. You can see recursive approach also. So same things, we are checking first empty things for the first element, and after that we are setting this temp variable to the first node self. Okay, and we are running a loop while temp.next does not equal to none. While this condition is not true, we are just shifting our temp to the temp next. We are repeating this process. So what happening actually? So we are setting our temp to first node, temp to this first node 10. Okay, 10 like this. So this is, I am just writing here. Okay, this is, we are just maintaining the reference, not the value. Temp equal to 10. Then we are checking temp.next equal to none or not. If it is not none, then we are moving temp equal to temp.next. So that means we are shifting our temp to this variable, this object. Now we are again checking temp.next equal to none or not. If not, then we are moving our temp to the next element. So temp will shift here. And here we will check temp.next equal to none. Yes. So if at any time we are reaching the node that contain the next field none, we will stop. Okay. And from this position, we will write like this. So temp dot next, and we will create a new object, node and 40. This 40 value we will pass. So it will create a new object 40, and that reference will be stored of this 40 into the 30 field. So in this way, this linked list will create. Okay, so this append I means a iterative version. So you can see after reaching at the last node, so this while loop will actually temp will move to the last node. And after reaching the last node, we are just creating a new object and linking. Okay, this object is created. Now we are storing the reference of this into this field, last node, next field. Okay, so in this way, we are just that linking all the object by the reference. Okay, and later we can search, we can traverse, because all reference we are storing into the previous element, and we can search all the element. Okay, so same things, head I we are calling now head dot delete 30. So delete operation is same thing. So if we have any list, so what is the delete operation required? Suppose we have some element head, and we have some like 10, then 20, then 30, and 40, and then 50, like this element are linked this inside the object, and we want to remove 30. So first things we have to search the 50, search the 30 things. Okay, so where is actually 30s exist in the linked list, and we cannot directly search because we are not using any indexing things. We cannot directly search 30 in the constant time here because we have only head pointer, head reference. So we can traverse the element from this first position, and we have to traverse all the elements to search any element. Okay, so we will start from the first node. It is equal to 30, no, then we will move to the next. It is equal to 30, no, then it is equal to 30, yes. Okay, so after traversing till this node, what is the operation required to remove this operation? So this is also an advantage of the linked list. Here we can remove any element in constant time after reaching at that node. Okay, so there is no effect on the other node like shifting or these things. We can remove in the constant time. So for remove this, what are the operations required? Just store the address of 40, reference or address of the 40 at this place, 20 next field. Okay, this 20 next field. Okay, so previous was the address of 30 is stored in the 20 next field, but now we will update this by the address reference of 40. We will copy from this 30 next field, we will copy this reference from here, and we will paste here. Okay, so now the reference of 40 is linked to the 20 directly, this, and this link is now removed, so this element will be removed. Okay, now if we are traversing the element 10, 20, then from 20 we have the reference of 40, then we will directly jump to 20, 40, and then 50. So this is remove the operation. So here you can see in the delete operation what we are doing. So this is I think, okay, this is fine. So first we are checking if we have empty list. So list is empty. If there is no element, we will return this, and then we will check if self.head.next equal to none. So here we are checking if we have only one element. Okay, so this is none. If V is the first node. Okay, so removing element, we are removing V, and this is the first node. So what we will do, we are doing here self.head.data equal to V, and self.head equal to none. Okay, not exist. Okay, yeah, we are removing this element. So for removing the element, so head is actually a first object that contain the first element. So suppose if you have 10 only, and you are removing 10 this. So what we will do to removing this, we cannot delete the object. Okay, because we have already created this object. We cannot remove the same object from the inside the object. So what we can do, we will just remove this value and we will just store none here. So this will also consider as a deletion of this element. So we are doing these things. If element is not exist, then we will pass this message not exist. Otherwise, we will traverse the list to search the element. Okay, so this is the base condition. If our element is not exist, if our element is the first element. Otherwise, if our element is not the first element, then we will traverse the list. So we are just assigning temp equal to self.head, temp1 equal to self.head, and by this help of this while loop, we will just traverse the element. Okay, and while temp.next is not equal to none and temp.data is not equal to V. So we are comparing the value also, and we are also checking that if we are what we will repeat this process until the last element. So every time we will just pass this temp1 equal to temp and temp equal to temp dot next. So we will repeat this process. In this way, we will reach the element v if exists. And after reaching the element at the v element, we will just update the address. So if temp dot data equal to v and temp dot equal to self dot head, again this is a if v is the first node of the list. So again this is the base condition. Here this is the main condition. Okay, so if our element is not the first element, so what we will do, we will just write the temp1 dot next equal to temp dot next. So what we are doing actually, so here actually we are maintaining two fields, so temp1, okay, and temp. So this temp will actually stop at the element which actually we want to delete, because we want to also read the address of this next element 40. So that is stored of the next field of the deleted element. So because of that, we are writing this temp1. So this is pointing to the previous element. So temp1 dot next. Okay. So that means this field 20 next field. We want to store the address of this 40. So this 40 address is stored at the place of 30 next. So this is actually temp dot next. So this is the update required. So we are copying the address of 40 from this location, and then we are pasting here. So this is performing by this operation by this line. Okay, and otherwise if element is not exist, then we are returning not exist. So in this way our elements are deleting. Okay, so this is one recursive implementation. Okay, this is given here, and same things we can perform with the two separate class. And you can see we have created the separate class for node, okay, and another class for the linked list. And we are just writing all the operation inside the linked list, and at the time if we need to create a object, we will call this class. So here this is so here not required to call the recursive thing. So here in the above code we are using the same class for the node as well as the operations, but here node is separate and operation is separate. So linked list, this contains the head, and if you want to, so here this head will remain separate. If you want to create an object, so we will create it like this. So L equal to linked list. So this L is actually a linked list. It will create a head, and head is actually there's no element. Okay, so this L is for linked list. Now head is object is, but this head is created now. Okay, one object is created, linked list object is created, and that contain the head field. And when we are calling this L dot append 30, so what happening actually, this head feed is actually containing the creating one new object of the class node, and this 30 will insert here. Okay, so L dot head is now referring to this first node. Then L dot append 50, so one new node will be added, class nodes, then 50 will store.
Sir, in the 58 line, if we put the entry inside the linked list part, then the head or the first element both created.
No, for this implementation we have not given any value for this. Okay, so this is just a linked list creation. So head only head will be created for this.
Okay.
Okay, so one object is created where the one object variable is created, L dot head. And when we call this function append first time, so the first node will be created from the separate class node, and that node we are adding with this head. So you can see the append function of this code. This is separate, so we are calling this. If self is empty, okay, so we are just assigning self dot head equal to node data. Okay, so that means if our list is empty, then we are adding first node. Otherwise, what we will do, we will check the last node by the traversing of the all nodes. Okay, so we are setting our temp to first node and then traversing all the node just by checking this temp dot next equal to none or not. Okay, so by this while loop, we are traversing all the element one by one, and we are reaching the last element with the help of this loop. After that, after reaching at the last node, we are setting temp dot next equal to new node. Okay, so suppose if we have like head equal to 10, 20, then 30, and then 40, because we don't know how many elements are there in previously. So, and we want to add like 60. So at the from the first node, we will check that which is the last node. Okay, so we will traverse all the node from the first. So 10, this is last. No, this contains the reference of some node. So 20, then 30, then 40. Now at the time of 40, we will check the what is the next field of the 40. That is actually none. So at that point, we will create a new object, and that we will store the 60, and we will store the reference of the 60 at the place of 40 next field. So in this way, this will be element will be added. Okay. So same things we will perform with the delete operation. We will check the element. We will compare the. So this is exact similar to the previous implementation, which we have explained. Okay. So both implementation you can see which you are comfortable. Okay, and you can also write your own implementation after getting the concept. Okay. So yeah, this is the linked list. And some advantages given the insertion and deletion operation are easy. Many complex application can be implemented easily, like tree, graph. Some disadvantages there. This is occupied more memory for the elements. Suppose if you want to store 10 element, so 10 element space is required. Apart from that, 10 reference memory locations are also required. Okay. So for one element, we are storing more memory compared to the normal data structure like data array or that list. Okay. So this is the disadvantage. Random access is not possible. So we cannot directly access the random element from any place. Some application you can see implementation stack queue, DQ. These type of implementation are easy or efficient with the help of this. We can also represent the graph, representation sparse matrix. Yeah, this is also one advantage of the linked list. What is this sparse matrix actually? Suppose we have some matrix representation. So this is also one example of the graph representation, and where most of the value are 0. We have lots of what is the size, like this is the 1000 rows and 1000 columns. Okay, and we are storing the value. So total number of places are 1000 into 1000. Okay, so this is the location we need to store the data. But in this matrix, most of the value are 0. Okay, like 10,000, or this is a total 1 6 time. Okay, so 10 lakh. Okay, so like 9 lakh value is 0 and only 1 lakh value is there. So most of the value are 0. That matrix is actually called as a sparse matrix. So what we can do, we can store the same information with the help of linked list. Okay, so I'm taking some small example to representation this. So like we have 3 by 3 matrix. So okay, so we have like 9 place. So 0 0 0 0 1 0 0 0 1. Okay, so in this place you can see more of the entries are 0. Only 2 entry we have with the 1 values. And so that means here if we are using this matrix representation, that means a list, nested list or something, this is occupying more memory. Okay, for the 9 place. But we can improve this with the help of linked list. So what we can do, we can store the data for this, and we will only store the locations. So this field. So what is we will create like linked list here, and we will store the data where the values actually exist. So what is this value? So 0 1 2 and 0 1 2. So where is the value actually? So 1 and 1 location. So we will store, we will create a node, and 1 and 1 we will consider as this value is 1. So this first 2 index is representing row and column, and this is the value. And then next data we will implement like this. So row is 2 and column is 2. So 2 2 and value is 1. So in this way we will only store the data which actually contains some value apart from 0. What are the row and column index for that, and what is the corresponding value? So we will store that sparse matrix in the with the help of linked list. So that will reduce lots of space actually. Okay, so this is just one application for this sparse matrix. And manipulation of polynomial expression. So polynomial expression we can also represent with the help of linked list. So like can create a linked list where so like this x equal to or some a equal to 4x square plus 3x plus 2. So like this type of equation, we can store the data for each representation. So what is the for this part? Okay, so we will store what is the value for this 4 and what is the power for this x, that coefficient value, so that we will also store 2. Okay, so this 2 value actually we need to store. This is the first constant value and this power value. Okay, plus next field. So this is constant value is 3 and power value is that 1. Okay. And next for 2, so constant value is 2 and this is 0. In this way we can represent the this polynomial expression with the help of linked list. So we can create the linked list for each polynomial expression, and we after that we can perform addition and subtraction with two polynomial expression with the help of linked list. So these are some example of you can perform with the linked list. Okay. Okay, is it clear that linked list concept? Any query in this linked list? Hello.
Yes, sir.
Okay. Okay, so this is linked list. So just try to implement this linked list by your own first for the basic operation, then move to the all operation. Okay, so yeah, I have some question for you. Now linked list, you know that. Suppose we have singly linked list. That this is question which is actually asked many times in the exam. Suppose you have linked list. One you have only this head pointer, and each element contain the address of next element. Okay, this like this. You have this structure, and this is the last element. Okay, suppose these are n element you have. This is the head pointer you have in only initially, and you can start traversing from this position. Now, some operation like if we are asking that if we want to add new element at the first position, how much time it is required? So what is the complexity for this operation? If you want to add one new element at the first position, if you have this structure.
Constant or big
Constant time.
Yeah, constant time, because you can what you can do, you can create a new object and you can just add the address like this and just change the address to this. Only two operations are required, okay, after creating the object. So this is a constant, big O one time. Okay. What are the time required to delete the first element? If you want to remove first element from the list, same constant, yeah, correct. We can just set the head reference to the second element, because we can directly read the address of second element from this first next field and copy to the head field. Okay, so this will be performed in constant time. And if we want to add new element in the last, what is the complexity?
Big O of n.
So this is big O of n, correct. Yeah, we have to traverse all the element from first to last, then we can add. Same things for the delete. Okay, delete last. What is the complexity required? Because if you want to remove this last element, you have to traverse all the element from the first, then after reaching at the last position, then you can remove. Okay, so these operations you can perform things, and same things from the between. If you want to remove any element from the middle position or anything, same big O of n time is required. So this is for this type of list. Suppose we have another structure like head, and now we have address like this, similar to the previous one, but this time we are also maintaining one tail, okay, that contain the address of last node. Okay, so we are also maintaining this. Now we want to perform some operation like insert first. You know that insert at the first position, will take, already discussed, constant. Okay, remove first will also take order of 1 prime. Okay, but what about the insert last? Now
We got
Order of
ones.
one.
Order of n, sorry.
Order of one, sir. Constant type.
Yeah, it will be constant.
we want to add one new element at the last position. So what operation are required after creating a new object? You need to
Order
just
of n.
no. You have the one tail this reference. No, you have the address of last node.
Okay, okay, sir.
Okay, so you can directly access the last element, and you just need to perform this operation. This add the reference of new object to this field. Okay, so it's stored like this, and update this tail reference to this new object. These two operations are required. So insert last will perform in constant time. But now what about the delete last? If you want to delete last element, what time is required and why?
Order of n, sir.
Yeah, we
N
have
minus
to,
one.
N minus 1. Any other answer?
it will be same, like we have to traverse through the list to find that element before that. So amendment.
Why you are traversing?
No, if you delete that one, we have to find the previous one. Right?
Yeah, correct. This is the correct logic. If you want to remove this, suppose if this is the last element now, this is the last element, and this is the none field. But if you want to remove this, you have to set something at this place. Okay, and you have to set none here, because now after removing this element, this will become the last element. Okay, this should be the none, and this tail should also be shifted to this node, second last node. But right now tail is pointing to the last node, and there's no way to find out the address of the second last one. Okay, because
But we can do so in doubly linked list, like in
so
view
no,
of at one time.
I'm not considering this doubly linked list. This is given in the problem statement, suppose. So in this case, delete operation will take order of n time, because to figure out the reference of the second last node, you have to traverse the list from the first position. Okay, and after reaching at this position, then you can delete this, and you can set the none value here, and you can set your tail to this position. So this operation is order of n. Okay, so just remember this type of things. This is asked in the previous exams. So doubly linked list is also the concept. So yeah, in the doubly linked list case, yeah, you can perform these things in the constant time.
Sir, in this case, why can't we make use of tail thing to find out the second last element?
No, you cannot figure out this. You cannot use this tail, because each element only contains the address of next element, not the previous element. Okay, suppose you have this list head, and each node contains the reference of next node. Okay.
Because we have to do the operation on the second last node. That's why.
So tail is referring to the last node right now. Okay, so this tail contains the address of last node, and we want to delete this node. We want to delete this node. So you cannot directly find the reference of second last node from the tail pointer, because tail contains the reference of this node, and this node not contain the reference of previous node. Okay, so you have to traverse the list from this side, first node to second, then third, then fourth, and then you will reach at the second last node. After reaching at the second last node, then you can set the none value here, because this node will be removed, and so after removing this will become last. So this tail should point to this last node. So for updating this will come. Okay, so the order of n is required. Yeah, in the case of doubly linked list, where each
So
node,
what will be the case for the middle element deletion or insertion?
Yeah, middle will consider as a order of n. Okay, because you don't. So suppose n element is there, so n by 2 operation is required. So complexity will become order of n.
For both insertion and deletion.
Any operation, insert or delete any. You cannot directly reach at the middle position in the constant time. You have to traverse at least half of the elements. Okay, so n by 2 operation are required, so it is equivalent to the order of n complexity. Okay, but in the case of doubly linked list, if head and tail is given, then you can perform insert first, delete first, insert last, delete last in the constant time. Because in the doubly linked list case, each node have previous address and next address. So from tail, if tail is pointing to the last address and last node address, so you can directly find the address from the previous field of this last address to this. Okay, so in that way you can perform the all operation in constant time, because where each node contains the first and last, the next and previous address. So you can move in both sides, left to right or right to left. So that is another case. So you can perform. Okay. So yeah, this is something important question which is asked generally. And apart from that, that stack. Okay, so stack, what is stack basically? Stack means, so you have already seen this example. Suppose if you have any disk case, okay, where one rod is there, one base is there, and you are just putting disk inside this rod. Okay, so here you can put the first disk, then after that if you are putting another disk, that will come on the top of this, then another will come on the top, then like this disk will be stored like this. Okay, but you cannot remove this first disk which is inserted first directly from this rod. Okay, you have to remove first this top disk, then you can remove the next top like this. Okay, so that means the last element which is inserted last, that will remove first from this structure. Okay, so that is called as a last in first out. Last in first out. Those elements are coming in last, that will remove first. So this is the restriction of this data structure. You can perform this insert and delete operation only in this way, or you cannot do any another operation directly. You cannot remove or element from any another position. So that means you can only use one side for insertion and deletion, both operation. Okay, so if you are implementing this with the help of linked list, so if you are performing insert operation from the end, so delete operation should also be performed from the end position. You cannot delete from the first. Okay, so that means this is the property of a stack. So that if you are implementing the stack data structure, this property should be fulfilled. Last in first out. Okay, only these two operations should be supported. This push operation means insert new element at the top. Okay, and pop means remove one element from the top. So if you are implementing this data structure and your implementation is fulfilled these two property for the push and pop, so that means your data structure is working like as a stack data structure. Okay, so this is the basic operation on the stack, push operation. So adding new element on one side, and from the same side, this is pop operation, removing the element from the other side, not another same side. Okay, so and traverse the element. So for the traversing element, you can only traverse from top to bottom. Okay, so top element, what is the top element, then next top element, like this. You can traverse the element in this way. So this basic operation should be fulfilled by your implementation. Then your data structure will be considered as a stack data structure. So this is like as a abstract data type. So that means abstract data type means like this list. Okay, so list by default supports some operation like this append. So how this append is working, that is actually hidden from the user. Okay, so how this is working, you are only using the operation. You are just calling this function and you are adding the element. Similar for this, if stack is given, so by default some operation is given to you, doesn't matter how that operation are performing, so that is actually hidden to you. You can only use that operation. So that two operations are there, so push and pop, or sometimes traverse or checking is empty or not. So this push and pop are the basic main two operations. So this push should be performed. That means on the one side insert new element, and on the same side this remove one element should be performed internally. Okay. So this is you can implement with the help of linked list, or you can also implement with the help of Python list. So here this implementation is given with the help of Python list. Okay. So what we are doing, we have created one class for the stack, and after that, at the time of creation of this object, we are creating one empty list. Okay, and we will only create it two operation or three operation for this. So this is push, this is pop, and this is empty. When we are calling this push object function, so we are appending one element. Okay, so appending means if we have list, and we will always the new element from add will add at the last place. We will insert the element from the end, append. Okay, so that means delete operation should be also be performed from the last. So here you can see inside the pop function, we are checking if our list is not empty, then we are calling the pop function. So this pop is also defined in the list data structure in the Python. So you can directly call this pop without any this index. Okay, so that will by default will remove the last element. Okay, so now we have created this implementation where two operations we have defined, and at the time of using of this stack, we will only we will call these two functions push or pop. When we are pushing elements, so 10 will insert first, then again we are pushing operation, 20 will be insert after this, and 30, and then 40. So 40 is now considered as a top, okay, in the list. And when we are calling this pop function, so this is the last inserted element, this will remove first. Okay, so this 40 will remove first. Again pop, then 30 will remove first. In this way, the operation will be performed. So this is the basic implementation with the help of Python list. Same things can be implemented with the linked list. So linked list we have just seen now. So the same operation. And now this is the node class. And stack, we have created this stack and is empty. This is the linked list checking push operation. So this push operation is just a append operation. Okay, in the linked list, we are appending the element from the last. So this self-return the top. Okay, top. Okay, node and pop. Okay, so here in the linked list, what we are doing, we are simply removing the first element. So if suppose top is the first node, like we are creating the linked list like this. Okay, we are inserting first element 10 here. Okay, if you want to insert 20 after that, so 20 will insert before this. So that means insert at the first position we are using as a push operation. So same from delete from the first position we will perform as a pop operation. So from the linked list. So if you want to insert 20, so 20 will insert at the first position. So this will become like top, then 20, and after that 10. Okay, if you want to insert 30, so it will become like top, and then 30, and then 20, and then 10. Okay, this is enough. And if we want to perform a pop operation at any point, so this will be removed first. Okay, so this first element will be removed. So why we are performing in this way? Because it is taking constant time. Because we are only maintaining this one top that is actually containing the reference of first node. Okay, so if we want to perform insert operation at the first place and delete operation at the first place, both can be performed in constant time with this linked list data structure. Okay, so we can perform both push and pop in constant time with the help of linked list. So this is the implementation. So push operation, we are checking that self dot is empty. If this is true, then we are just removing the node dot data. This is for insertion. Okay, so we are creating a new object for the class and we are setting to top equal to new data. Otherwise, what we are doing, we are just using this temp equal to node dot next. We are calling creating new data. Okay, set dot. Okay, yeah, this is the first position insertion. So temp equal to new object creation. After that, temp dot next equal to self dot top. So we are just adding one new node at the first place, and we are setting self.top equal to new, which is new element which we have created. Okay, so first place insertion. So this is taking constant time. You can see we are not running any loop or anything. So same things with the pop. We can remove the first element in constant time in just 3 steps. Okay, so this is just implementation of the stack with the help of linked list. Now queue data structure. So this contains the property of first in, first out. Okay, so that means if we want to implement a data structure that will follow this rule strictly. Okay, so insertion operation will perform on one end, delete operation will perform on another end. So that means those elements are inserting first, will remove first. Those elements are inserting at last, will remove at the last. So this first in, first out, this property should be fulfilled by our implementation, and then that data structure will be called as a queue data structure. So this is just a diagram. So you are in queue. So the name of this operation are in queue and dequeue. So in queue means insert a new element, and dequeue means delete a new element. And sometimes we are also use the term front and rear. So front is represent as the element which will remove first. Okay, which will remove, that is called as a front point, and this back or sometimes rear. So rear is a last position where we will insert the new element from this side. Okay, so front side element will be removed, from rear side element will be insert. So this is just a indication. So here same things we can implement with the help of the list, Python list. So you can see the same implementation. We are using queue and we are created one list. For in queue operation, we are appending the element at the last position. But for dequeue operation, you can see we are inserting the element at first position. So that you can see self.queue equal to okay, so this is inserted like q0. Okay, so self q0. Okay, this is remove thing. Yeah, okay, yeah, we are removing this element. So what we are doing, we are just reading the data at the first index, 0 index, and after that we are setting the self.queue equal to self.queue after this indexing 1 dot. Okay, or what you can do, you can also perform this operation by this just pop 0 index. Okay, so in this way you can also perform this. So that means from list element it will insert from the last but remove from the first index. So that should be operation should be performed, and these two operations we have created for this class, and that we can use for the operation only, and we cannot perform any other operation, like we cannot insert in between, we cannot remove from between like this. So this is the strict definition of the queue. So after this queue, so this type of question is also asked. Some sequence of the operation will be given to you and will ask that what is the current state of the queue. So like this sequence of operation if you want to perform, so 10 will insert first, then in queue 20, so 20 will insert after that, 30, then 30 will insert after that, 40 insert here. So this is now rear element and this is front element. Okay, now we want to perform dequeue operation. So dequeue will remove the element which is inserted first time. So this is actually the remove first time. So this inserted first time, this will remove first. Okay, so this 10 will remove now. Now the remaining element we have this. So now front will point to this 20. Again we were performing dequeue, so this 20 will remove. And now we have remaining this element. So this is front and this is rear. Okay, 30 front, 20. So if you will print Q, so 30 and 40 will come in the output only. So same things. Now we can implement with the linked list with the help of linked list. But here to implement this, so to insert element, you can use one side, one point either first position or last position. Okay, so if you have linked list like this Q, so what you can do, you can insert the element at the last position. So like from this position, but you can remove the first element from the linked list. So here in queue operation, what we are doing, so in queue is empty front. So yeah, So for insertion we are using this first position, and for DQ you can see what we are doing. Okay, so let me, what a field we are maintaining, temp or next. Okay, yeah, so for this data structure actually we are maintaining this front and rear two fields. So front for first element and rear for the last element. So like this head and tail, we are maintaining front that will contain the reference of one first node of the list. Okay, like this. And we will also maintain one rear that will always contain the reference of last node. So with this help, what we will do, we can perform both operations in constant time. So we will insert the element. We will insert the element at this position at the rear in constant time, and we can remove the element from this front side, the constant time. So this is we are using the same linked list 2 operation here. So insert at the last or remove from the first. These 2 operations we are using, and we are just implementing the queue data structure with the help of linked list. So if you see this in queue operation, so here you can see we are just directly performing rear insertion. You can see rear.next equal to temp. Okay, but for DQ we are removing the element from the front. So we are using this front equal to self.front.next. It's setting our front to the next element. So both operations are performing constant time. For traversing the element, we are just traversing from that first front to the rear side. So this is the traversing things. So same things, what is the operation will perform? So 3, 40 will come after that, 50 will insert, then 60, then 70. When we will remove this DQ, so this will remove first, then this 40, this 50, and this 60, and 70. So all deleted. And for this operation, it will show the queue is empty. So print none. This will print none. Yeah. So this is regarding the queue data structure. Any query in this stack and queue? Anyone? Okay, so no query. Then we will move to the hash mapping. So hash mapping or hashing, sometimes we use the hashing. So this is also a very important concept where we can store and search the data in constant time with the help of some hashing function. And this hashing concept is actually used by the dictionary data structure in the Python. So when you create any key like this D, if you have created like dictionary, and for D you are storing like k equal to, or any like 5 equal to 10. So this key, this data will store in constant time in the memory. Okay, how this will perform in constant time? So some hashing function will be used internally, and that hashing function will create a memory index or memory address with the help of this key value. Okay, that hashing function is just a formula, so that you can see this figure for storing the data. So this key actually which we want to store in our memory. Okay, this is a data, and we will use one hash function. This is just a formula or encryption things, any formula we are using here, and that is taking this key as a input and returning a value which is indicating the index or in the hash table. Okay, so directly returning the index, and that hash table index is actually storing the memory where the data is actually stored. Okay, so what, like for example, if we are using the mod function, so that mod function we and reminder value we will use as a index. Suppose we have the size of this hash table 10. Okay, and we have total 10 index 0 to 9 for this side, total 10 index to store, and we want to store 21, and this is a key. Hash function we are using key mod, and total size we have 10. Okay, so this formula we are using to generate the index. So what we will do, we will pass this 21 as a key here. So 21 mod 10. So what reminder we are getting? 1. Okay. So that means this 1 is representing as an index in the table. So we will directly jump to this index and we will store. So this is linked to some memory space, and that is contain the key and both things. Okay. So this, what is the corresponding key? So this 21 and corresponding value. What value we are storing? So some memories are linked to this. That data we will store. Okay. So this is the way to generate the index in our hash table with the help of data. So we are directly calculating the address, or we can say that the index of the hash table by this data, and directly moving to that index, and we are storing our data. At the same thing, on the searching time, we suppose if we want to search this 21 into our memory, so same process we will apply again. Okay, so we will pass this 21, and this 21 will be supplied to this hash function. So same this function, and this hash function will directly generate the index 1, and we will directly look that index, what is the value, corresponding value for this key. So this 21 key will be stored at this index, and corresponding value will also be stored, and we can directly read this data. There's no need to traverse all the data from first to last like this. So this hash function is basically generating the index directly, and we are directly jumping to that index to get the data. Okay, so this concept is actually used for the hashing, and this hash function may be anything. So any formula it can, so maybe any complex formula can be used for this hashing function that actually generate the memory location or index things with the help of the data directly. And same hash function used for the searching. So both storing and searching operation can be performed in constant time with the help of this hashing function, hashing concept. But there is one problem with these techniques. What happens, suppose for this formula we have 10 location, but we are storing the data, and we have stored this 21 first time. Okay, 21 is stored at this location, one index. What happens if we are storing 41 again? Okay, now 41 is again will generate the same index 1. 41 mod 10 will again generate the index 1. Now we have already stored the data at this one index, and we are getting the another data for the same index. So that is called as a collision. Okay, and this is called as a collision situation, where we are getting the same index for two data. So some resolving, the collision resolving techniques is actually used. One technique is this open addressing and close hashing. So in this way, one technique is linear probing. So linear probing, what is this? So we will increase the index one by one. So suppose if you are getting the collision, then we will check the next location after this. Suppose for this 41 we are getting the same location 21, so we will check the next location just after this. So after we are getting 1, then we will check the next location 2 is empty or not. Okay, if 2 is not empty, then we will move to the next third index, so that it is empty or not. So in this way we will check linearly one by one each location if we are getting the collision. So if suppose here 2 is empty, now we will store 41 here. And after that, suppose a new data is coming like 62, and 62 again we will get the collision because 2 index we will get. Now 2 is we have used for 41. Then now we will check the next location 3 for this. 62 will store here. So for remove this collision things, we will use this technique linear probing, and after getting the collision at any index, we will check the next index. That is called as a linear probing. So this is one technique. Similar things, linear probing, this is different, and same thing quadratic probing. So quadratic probing, here we are incrementing one by one. Okay, so like after getting the collision on one index, we are moving to second, then the third, then fourth, like this. Okay, so sometimes what happen, maybe all continuous position are actually occupied. So what happened, we are checking one by one, it will take more time to get the free memory location. So what we can do, we will not check one by one, we will check some after skipping some location. So that we can decide by this formula. So first we will check h. If we are not getting this free location, then we will check for h plus 1. If this is not free, then we will check for h plus 4. So this is basically h plus I square. Okay, so this I square, and I we are passing like 0, 1, 2, 3, 4, 5. Okay, so h is the base index that we are getting from the hashing function. After that, if this is not free, then we will increment this I by in this way, and this will be increment in this square things. Okay, so I square. So when I equal to 1, so h plus 1. When I equal to 2, so it will become h plus 4. So that means if h plus 1 index is not free, then we will directly jump to this h plus 4 without checking h plus 2 or h plus 3. So there is a chance to get free location in less steps.
Sir, just one doubt there. So this hashing function or hashing technique, it is used by the Python itself, right? Wherever
Dictionary.
Yeah, dictionary and string, wherever this immutable concept is there, right? Like there.
No, not string, dictionary only.
Okay, only dictionary key value will be using the.
So that dictionary key value will be stored using this hashing things, and corresponding value we will also store at the place of a key. Okay, because we actually access the data, we search the key. You cannot search the value directly in the dictionary. Okay, suppose if you have dictionary D where you have the data like 1 equal to 1, 2 equal to 4, like 3 equal to 6. You cannot directly search this data, this value field. You cannot access this, but you can access this field, key field directly. You can directly check 2 in D or not. You can directly check.
So any other data uses this hash function in whatever we know, right? I mean, list definitely does not use. So
the list is not used. Yeah.
Set and tuple is there, right? Whether set and
so this first thing, dictionary, this use this hashing concept. Okay, and sometimes this set is also, I think, used. Set is also used this hashing internally, because you can also search the data in constant time in set. But yeah, I'm not sure about the set implementation, but definitely this dictionary is actually used this hashing concept.
Okay.
Where you can.
Okay, and one more doubt there. So if some customer, if we are using the hash function for storing some data, in that whether any requirement may be there that we need to do the indexing on top of the hashing in a customer.
Yeah, here actually you're getting the data in constant time at any years with the help of this key. Yeah, so sometimes what happen if that indexing thing is by default. If you're using this Python, by default this indexing is assigned to this. Okay, if you only want to store the data and you don't have any information like as a key things or value pair like these things, so in that case you can use the list and you can directly access the data with the help of this indexing. But sometimes we store the data with the pair data, like this key value pair, where some values depend on the another value. So in that case, you cannot access the data with the help of index, because the index doesn't have any meaning. So key is actually some meaning in your data. So like if you're storing some, you will see this type of representation in the data, this graph unit, that week 4 or week 5, where you will see this implementation, like you have two node V and U and V. Okay, so and you want to check that U and V, what is the distance, so that will be stored in the dictionary format. So U will be created as a key, and inside this distance, the V and what is the distance, that will be stored as a value. You can directly check this what is the node where you can directly jump from U by the help of this key U. So this type of data where the key or value both have some meanings, okay, and you want to access directly that data. So you can use this dictionary where indexing is not helpful, because indexing is by default assigned from 0, 1, 2, 3, 4, 5, 6, where you cannot figure out that what 0 is meaning, what is 1 is meaning here. And you want to store the meaningful data in your dictionary, and you want to perform constant operation on the searching and storing, then you can use this dictionary things.
So, so is it like in the hash map, it will have the index will have the keys, and anytime if we are trying to retrieve the data, first it will go and check in the index whether this key is there, and then go to the value like that?
Yeah, so you can, if you're checking if D in key, if key in D, then you can perform the things. So that D in key is actually will perform in constant time. Okay, so like any dictionary key, so if you want to check this 3 exists in the dictionary, so just check 3 in D or not, or just use this condition. If 3 in D, just read the value. What is the value corresponding for this? So this in D operation is actually performing in constant time. But same things if this D, if you are using L list, okay, then this operation will take order of n time.
Right. So in case of dictionary, it is irrespective of the position or the what key, it is always constant, any element.
So this is actually a user-defined index. You can say that this is user-defined index where you have some meaning for the index. Okay. So this is not a by default index of the data structure.
Okay.
Okay. Yeah. So this is one way to remove this collision. So you can use either this linear probing and quadratic probing. Another is this closed addressing and or open hashing. We can see that. Yeah.
Sir, in the dictionary index that you said, so let's say there is 100 keys. So how it is finding constant time?
So using this hash function, na. So suppose 100 keys are there, but each index is actually generated by the hash function.
But sir, hash that figure has to match that digit, whatever it is generating.
No, actually, what happened? We have one hash table where we have assigned this index 0, 1, 2, 3. This data structure we have internally directly. Okay, and this hash table contains some index numbers. So 0 to like 99 or depends on the memory location available. And in between we are using hash function. Okay, at the time of storing the data, we are passing the data to the hash function, and this hash function is generating the index based on this data value. And at that index, we will store this data like this. Okay, and the same type of the searching, we will pass this data to the hash function again, and this hash function will generate the same index. And we will directly look that index and we will check our data. Okay, we are not searching any data. Yeah, so worst situation is there in the dictionary also. Suppose that is actually in the rare cases happens. So what happens? Suppose all this data are full actually. Okay, and we are using linear probing for the collision. Okay, and we are getting the first index as this is filled. This is already filled. Then we are moving to the next index. This is already filled. Then we are moving to the next, and in last we are getting the free space. So in that way, we are traversing all the elements that it will take order of n time. So this is the situation when we are getting lots of collision. But this is not happen most of the time because we have the big memory space, and we have this hashing function. This is also not very basic hashing function. This is also a very complex hashing function. This rarely generate the same index. Okay, for two different values. So this hash function is very complex. Formula techniques is used that is actually rarely generate the same index for the different values. So that is also one thing. Okay, but yeah, this is the conceptually this is also a case where this dictionary worst situation is order of n time, but we generally ignore this. Okay, so yeah, this is another way to remove this collision with the help of this chaining method using linked list. So this is another example of the linked list. How we can remove this collision. So in here we can store the data with the help of linked list. So like this is the index, okay, and we are hashing function is generating this index for two different values. So suppose we are passing 40 value and we are getting 0 index for this. So what we will do, we will create the linked list for that, and we will add this linked list for this 0 index. So 40, we are adding this one first element. After that, again, if we are getting the same index for another element 60, then we will add this 16 element to the linked list which is connected to this 0 index. So all elements which we are getting the same index 0, that linked list we will create, and all element we will insert in this. All element which we are getting 2 index, we are creating another linked list, and we are adding all element inside this. So 32, 22, like this. Okay. So in this way, we will store the data. So at the searching time, if we are getting 0 index, we will just traverse this linked list. So this is one way to remove the collision problem. We can also store the data with the help of linked list for the same index value. Okay, so this is called as a chaining method using linked list. So these are some basic of the hashing. So just we have not discussed in much detail, but the basic idea we have discussed in the Week-3 hashing. So how we can achieve the constant operation in searching and that is storing the data. Yeah, this is all topic of the Week-3. So any query? So our TA will discuss some previous year question based on the Week-3 concept in coming session. Okay. Yeah. So any query?
Yes, sir. I have one query.
Yeah, please.
You please go to the GitHub.
GitHub page where?
Yes, linking that is using one class. That code.
That linked list with the help of one class. You're saying?
One class. Yes, sir.
Okay, moving to that. I have this here also linked list. Yeah, this one. This one.
Line number 67. It is 10 equal to 7.
67. Display.
Sir, under that else, line number 67.
Line number 60. This one.
No, sir, 67.
67. Okay.
What it is doing, sir?
Okay. Let me remove this. Okay. So this is a display function where we want to traverse all the element from first element to last element. Okay. So first, what we are doing in this code, so self dot is empty. So this is empty function is just checking that first element is none or not. If this is true, we will return directly none. That means no element is exist in the list. Otherwise, what we are doing this, we are setting our variable to the first node. So this is a recursive implementation. So when we are calling this display function, so by default this is called from the head. Okay, so head dot display. So this self is actually referring to the object head. Okay, and that object is actually a first node. Okay, so head object is also referring the first node.
But sir, how it is just saying self out?
So self is always referred to the current object where it is called actually.
Yeah.
So if we call this head dot display, so this self is referred to this head object. Okay, so this self variable which we have used inside this constructor at the time of creation of this object. So this self is actually this is a reference to the current instance of the object. Okay, and when we are writing this self, so that means this is just referring to the same object head.
Okay, is it storing the location value or something like that?
This is a reference. The reference means we can say that as an address.
Okay.
Okay, so what happened? We have created one head object. Okay, so head is just a one object it is created, and that object contains some memory spaces that is for value, and that is for next. This memory space it is created when we created this object, and this head is just referring to this memory spaces. Okay, head dot value you can access, head dot next you can access. Okay, so this head is just as a referring to the first node of the list. Okay, and when you are writing this temp equal to self, so self is also referring to the same first node. So head is referring to the this memory space, so you can also referring to the same object. So temp is equal to self, this is means the same locations.
Now it is clear.
Okay, then after that we are just traversing all the elements. Temp does not equal to none, we are just shifting this temp to the temp next. We are just shifting to the next object by the reference.
Yes, sir, that is clear.
So the self is the current instance or current object. Okay. Okay, any other query?
Hello, sir.
Yes.
I joined in late. So, doubly linked list is done or what?
Yeah, doubly linked list is not discussed in detail because conceptually we have discussed. The only change is actually we are maintaining address of the both side actually for the each node. In singly linked list, we are only maintaining the address of next node. Okay, data and next. Okay, but for doubly linked list, for each node we are maintaining this 3 field data and address of the previous, or we can say that the reference of the previous node and reference of the next node. So this part we are maintaining, but we are also maintaining the previous data reference.
Yes, sir.
So at the time of creation, you can maintain both linked. Okay, so it's like head. So HEAD head at the time of first creation. So each node will contain the both address. Okay, so previous is none. So none is there. Data 10, like we are storing 10, and this will contain the address of next node. This will contain the address of previous this node, and like 20, this will contain the next. So each node will contain next or previous. Like this.
So, there's a question in PRP actually. So, is there a code for this? How to do this? Like, there's a.
You can easily do. So what you can do at the time? Let me just open the code. So what modification you can do?
Yes, sir.
So like this, I'm just showing this second implementation. So in this using two class, for this class node, what you can do, you can take one more field, self dot tvs. Okay, equal to none. So this is one modification. This is for the node because we are maintaining 3 field for the each node. Now inside the linked list, at the time of append, when you are appending the data, so at that time what you are doing, you are only storing the temp dot next equal to new node. Okay.
Yes, sir.
But what at the time of new node addition, so you have the head, and suppose if you have a new node, if you have added at the first time, so you will also save this. Suppose this is a temp. If you have created new object with the help of temp, so temp dot previous, you have to store that like prev equal to none because there is no element after that. And temp dot next, you are storing the new node like this. So at the time of insertion, you have to fulfill this all three, all these two reference, previous or next. Okay. Now in the singly linked list, we are only storing the reference to the next node. But here for the doubly linked list, you have to store the reference of the next node as well as the previous node. So that instruction will also be added.
Yes, sir. Sir, it would be great if you provide the code in the TA sessions as well. Is it possible?
Doubly linked list implementation?
Yes, sir, please.
Okay. So when is the TA session for this?
Tomorrow, I guess. Tomorrow is the TA session.
Okay. So by tomorrow, I'll try to create.
Yeah, if possible, you can. We can also do it in the next to next TA. It's fine.
That is fine. I'll try to write the code by tomorrow also. Okay, so I'll just pass to the TA.
Yes,
And
sir. And sir, is stack and queue covered?
yeah, stack and queue we have discussed.
So, sir, in queue, there's also one more concept named circular queue and DQ as well.
That is also there. Yeah,
Also,
so the
that is
conceptually, yeah, okay, conceptually, what is the circular queue?
yes, sir.
So circular queue is just like a like this indexing these things. Okay, so suppose we have
Sir, isn't there a circular linked list also?
circular linked list. That is also one type of linked list. So what happened in the circular linked list? So last element actually not contain the none field. Okay, in the circular linked list, that will contain the reference of first node of the node, like this. So linking is happen like this. Okay, so suppose this is a head and this contain the first node. So last node will not store the none value. It will store the reference of first node. So that means you can traverse the list, and after the last node, you can directly come to the first node. So that is called as a circular singly linked list.
So where
And
is this useful?
This is just based on the depend on the problem. If sometimes if you want to traverse the list in circularly, right now I am not able to recognize the application for this, but it depends on the problem. At any time, if you want to directly jump from last location to the first location for the process.
Okay, sir. Okay. So, and so in the videos in linked list, we had append and delete at the start and end. But if you want to append in the middle or delete in the middle, then what should we do?
So you have to first thing you have to figure out what location you want to insert. Suppose if you have list the head and you have some element already in the list. Okay, I'm writing element also 10, 20, 50, 60, 70. Okay, and this is like none. Okay, and you want to insert the element on third position. Okay, so this is the third position. So what you will do, you will take some counter. So counter will set like as a 1 to this, and you want to insert at the third position. So position equal to 3. You will have to maintain, and because this list is a singly linked list and head is contain the reference of first node, so you will maintain one variable temp that will contain the first node address. So this is head. That means temp will set to here. Okay, now you will traverse the list to reach at this position. This position means you have to reach this position, 1 less than this, 3 minus 1, 2. Okay, so to maintain this, you can just maintain temp equal to head, and you can also initialize this k equal to 1, and you can run a loop while k is less than POS. Okay, while this condition is true, just perform this thing, temp equal to temp next, temp dot next. So what is the meaning of this? You are just checking k equal to 1. 1 is less than position 3. Yes, correct. So just perform temp equal to temp dot next. So this is the temp dot next. So that value will be assigned to this field. So this is reference actually of this second element. So temp will move to this node. Okay. Now increment the k value. So k equal to k plus 1 in this loop, and k will become 2. Okay. Okay, so we have to modify the condition also. Otherwise, this 2 is also less than 3. So that we want not perform. So we have to write the condition k is less than POS minus 1 only. Okay, so in this way, you will reach at the node which are coming before the insertion position actually. So this 20, this node you have to reach if your position of insertion is 3. So that means new node should be inserted after this 20. Okay, so if you are following this condition, k is less than equal to POS minus 1, so only one jump will be there, and then you will reach at here. After that, your k will become 2, and 2 is not less than equal to 3 minus 2. So your loop will stop. And after reaching at this position, what you can do, you can create a new object. Okay, and create a new object here and store the data. Suppose if you want to store 40, so just store the data here 40, and link this data. So temp is referring to the node 20. To insert this 40 in between here, so what you need to store, you need to just update the address. So the address of this 50 node, where is this address stored? Here, this 20 next field. Okay, so temp dot next. So what you can do, suppose this node is actually a new node. So what you can do, write like this, new node dot next. Okay, so new dot next field is referring to this, equal to temp dot next. So temp dot next is a address of the 50. So this address will be stored at this location. So this means this will link logically to this. After that, second change we will do, we will store the data of this 40. So this temp dot next, this is the location. We will store the reference of new node. So new node we will write here. So new node. Okay. So this new node reference will be stored into the temp dot next, this field. Okay. So this will update by this address. Okay. So logically this address will be changed. 20 will be linked to the 40 and 40 will be linked to the 50, and new node will be inserted in this way. Okay, so this address modification we need to do only. So after reaching at the correct position, just update the reference field, and then your insertion will be happen. Same things you can do with the deletion operation. Suppose if you want to remove this 50 from between 20 and 60. So what you can do, you can just search this 50 first, okay, by the traversing each element one by one, and stop here. Okay, so suppose this temp is stopped here. After that, you have to also maintain one more pointer, which is actually will shift one previous position to this temp. Okay, this temp is referring to the delete node, and temp previous, like you can maintain for the location for the previous element of this temp previous. Okay, so just move your pointer in this way. So this pointer will set in this order. Okay, so temp will move to the deleted element, and temp previous will point to the previous element 20. After that, what you need to do, you need to just update the address. So you need to store the address of 60 in the field of 20 next. Okay, so address of the 60 is currently available in this 50 next. So this is you can read by the temp dot next. So this temp dot next will be stored in the temp previous dot next. So you can write like this instruction. So temp previous dot next equal to temp dot next. So this temp dot next is 60, referring to this one, and this reference will be stored into this temp previous dot next, so this field. So this will be logically linked to directly 60, and this reference will be removed. So 20 will be linked directly to 60. So 50 will be deleted. So by this address modification, you can do the task, this insertion deletion. Okay.
Sir, understood. Sir, but if possible, if you add this code as well in the PDF along with that, so it will be
so
great.
This is already there, na? Delete operation or middle is not.
Yeah, middle and appending as well. Inserting, I mean.
I think it is there. Okay, insertion is not there. I think in between.
Okay,
but
deletion.
yeah, deletion is there.
Okay, sir.
So you can see this deletion V. Let me just this is append I this insert, you delete this. Okay, so this delete is actually V. What we are passing the any specific element value.
Okay, sir.
So this deletion is performing that operation deletion, but inserting in between is not there. So that position code is not there. Then we can add that code.
I guess it's a bit late now, but can we discuss the DQ and L circular queue tomorrow in the TA session?
So I am not sure about the TA know this. Otherwise, the circular queue and DQ. So DQ, let me just explain. So conceptually, DQ is just a data structure where the operation of this insertion and deletion can be performed from both sides.
Yes, sir. Yes, sir.
Okay, so this insertion and deletion, and same things from this side, insertion and deletion.
Yes, sir. I've heard
so
about it.
Yeah, so this you can just simply create the DQ implementation with the help of Python list. Okay, so what you can do, you can perform the insertion from this side. You have to maintain these things, DQ operation on the left. So you can just give the option to insert from the end or delete from the end. So insert from the end means append operation. Delete from the end means pop operation of the list. Okay, and
Yes,
insert from the first position. That means you can directly use insert operation of the list. That means you can pass the I think some insert operation is there. I'm not sure about this insert operation. So what parameter is required? So I think index is
the
required and
element,
values.
yeah, the index and element.
Index and element is required. So just pass 0 index and element. And for delete operation, just pass pop 0.
Yes, sir. This is the direct implementation. But if I want to know the internals of it, so that's why I wanted to know.
No, this is the for DQ. DQ conceptually is this. Okay, so insertion from both sides and deletion from both sides. Then you can implement this with the help of another data structure like this Python list, or you can also implement with the help of linked list. But your operations should be restrict according to the concept. Okay, so if you are implementing DQ, only these operations should be supported by your implementation. You cannot insert in between, or you cannot remove from between.
Okay, sir. Yeah.
Okay, so this restriction should be there after implementing your that implementation your data structure. That only these operations should be supported.
Okay, sir.
Okay, so on the GitHub notes that stack and queue implementation is given. So you can see this implementation of queue.
Yeah.
So here we are implementing, we have created one queue class. Okay, and we have only defined these two functions, inQ and DQ. And these two operations we can call from this and any object of this queue class. So this means this implementation only support these two operations, and these operations can be performed only according to the queue concept.
Okay.
Okay, so that concept should be fulfilled by your implementation. Then data structure is actually a queue or stack.
Yes, sir. Just a small question. If I'm giving an interview in some company, so what are the main structures they will ask? Like, you know, any like main concepts should I know that?
Yes, so these are all actually required things. So they can ask anything. So I'm not sure which one is the important. Okay, so they can ask anything. So you should know about all the things. So what is like they can ask what is the concept of stack. So you should know what is the concept of stack. That means last in first out.
Yeah.
This is the one word concept actually.
No, sir. But in industry, what all things mostly are used? Like which data structure is used the most?
That is also depends on the problem. So suppose if you are performing any problem which is actually is more comfortable with the graph data structure, then you can use graph. You cannot use the list at that place. That is based on the problem statement. This is also not based on the company.
Yes, sir. Just I heard the additional DQ and all. That's why I asked. So is that of important? Like, is that important? Like DQ, circular queue, and all.
You can explore this if you have heard this. This is also they can ask in the exam. You can also see that some question in the competitive exam.
Yeah, actually, in 11th, 12th, I had Java. In that, there was a part for it which was cancelled actually. So this was there in Java, DQ and Q, circular queue, but it was not taught in the class. So that's why I asked here.
These are actually data structures. Okay, and these are data structure, and we have more data structure also. So this is not only the these data structure. So all are not covered in this course. Some algorithms are also not covered in this course, like B-tree is not covered. So you can explore other topic also if you but after completion of this course first.
Yes, sir.
Okay. Yes. So first complete this course and clear all the concept of this course. After that, you can explore the related more topics which is not covered in this course.
Actually, there's an advanced level course in this degree as well, advanced algorithms.
Advanced algorithm, but this is that is actually related to this dynamic programming, greedy algorithms. That is not related to the data structures.
Okay.
Okay, so that are actually more advanced concept regarding the algorithm design techniques like this.
Okay, sir. Okay. So I should learn by myself, like all the other.
So this data structure you can learn by your own. So like this queue and what are these things. So these are actually a little bit concept change only. So like the circular queue, we are just linking the circularly, and similar for the circular queue is also similar. So for the circular queue, we treat like this. Suppose if we are implementing any circular queue, so we treat the address like this. Okay, so suppose we are implementing by the help of linked list, okay, or list only. So this is 0 index 1 2 3 4 5 6 7 8 9 10. We have the size of 11 element for this. Here we are using this list data structure with 11 element, and we want to implement with the treat like as a circular queue. So that means when we are inserting the element, okay, so this element will be inserted like this 10 20. So this is front and this is rear, okay, and we will insert element always at the last after the rear. So 30 40 50 60 70 80 90, okay, and 100 or 110. Now this is full. Okay, now this is full, all element space are filled here. So how we can do, suppose what happened, now this is the last index of this array, and we remove one element from this. Okay, now this will become front and this will remain rear. So what should happen, if we check this is empty or not. So according to the concept, this is the last index, and we will check there is no index after that. There's no 11 index after that. We have the limited this last index. So our algorithm will show you that our queue is filled already fulfilled. Okay, but we have removed one front element from here. So this one space is actually empty now, and we are not using this because we are not using circular queue. So our last index is filled. We will show you that our actually data structure is completely filled. But what we can do with the help of this circular queue concept, after getting the last index, we will check the first index. So how we can do this? So this rear is actually representing 10 index. Okay, so this 10 index is referring to the last index of the data structure. So to calculate the next index, what formula we can use? We can use this r equal to r plus 1, and what is the maximum size of this? Okay, so maximum size we have a total 11 element. So that what is the remainder value of 11? Okay, so what is the current value of r is 10. 10 plus 1, we are getting 11. 11 remainder 11, we are getting 0. So after 10, after r, if we have reached r equal to 10, then for next index we will check 0. Okay, so we will use this formula when we are inserting a new element into the queue. Okay, so if suppose r equal to 9, so we will use the same formula, r plus 1 and remainder the length of the data structure. So this is 11. So 9 plus 1 and remainder 11, we will get 10. Okay, so 10 is the last index. But after 10, we will get 10 plus 1 and remainder 11. So we will get 0. So that means we will come to this location if this is free. If this is free, then we will insert our new element 120 here. Okay, so that means we can remove the element from the front side and we can insert the element from the rear side, but rear will not stop at the last index. Rear will just traverse like a circularly, and after 10 it will come to the 0. So in this way we will utilize all the location if any location is free.
Yes, sir.
So this is the concept of that circular queue.
Yes, sir. Understood. I'll go through the code later in the.
Yeah, you can just try to implement this concept. Just take some fixed size. Here, actually, fixed size data structure is required. But in Python, actually, we have this dynamic list. So there is no problem we are getting actually related to this index things. Because of that, some implementation are not covered. Actually, this circular queue is not very much relevant for the Python.
Yeah, yes, mostly in Java and C++ because they use arrays. Yeah.
Yeah, they use the array and they have the fixed size actually.
Yeah, yeah. Understood, sir. Thank you, sir.
Yeah. Okay.
Thank you, sir.
Okay, then. Bye, everyone. Thanks.
Thank you, sir. Good night.
Thank you.
Good night.